Okay. All right. So very good evening all. In the yesterday's session, we discussed about the thermal modeling of the SCR and the gate characteristics of the SCR, right? Also, we discussed the protection of the SCR. So as long as the protection of the SCR is considered, we need to protect the SCR against over voltage, over current, right? High dU by dt and high di by dt. Apart from these four protections, we need to protect the gate cathode circuit also. In the gate cathode circuit, we are having over voltage protection, over current protection, okay, and protection against the noise signal, right? So all these 7 protections plus in addition, we are using the heat sink. Heat sink is to limit or to control the temperature of the device, right? Next, now before moving towards the discussion regarding the numericals on calculation of the snubber circuit, there is one mistake from my side in the yesterday's session. Yes, actually the thing is in this question, right, you can check the question related to the gate cathode characteristic, right? In this question they have strictly mentioned that find the value of series resistor RZ to be inserted in the gate circuit to limit peak power dissipation. Okay, peak power dissipation. So that's why here instead of the average power we are supposed to take, yes, maximum power here. Okay, so here instead of this average power we need to take the maximum power, right? So please correct it. Actually the thing is yesterday I directly solved this second bit, okay, and yes, actually I did not consider this bit, that is that RZ was related to the for the limiting the gate power dissipation, peak gate power dissipation. Okay, so please correct it. In the notes I have corrected it. In the class notes you might have seen I have corrected that, and after correcting we'll be getting the final answer as 6.92 ohm. Please correct it, right? No, pages are not missing in the yesterday's notes, right? Okay, okay, right. So please correct it. This is the problem regarding the gate cathode characteristic. Okay. Yes, yesterday's PDF, if it is not in proper sequence, I will check it once and I will re-upload it. Okay. Yes, correction means the thing is only here instead of this PG average, na. Yesterday while doing calculations, we considered this PG as a PG average, but they have strictly mentioned in the numerical that yes, to limit the gate maximum, to limit the peak power dissipation, na. So that's why we need to consider it as a peak power. PG max we need to consider, right? So PG max they have given it is a 5 watt, so we need to consider it as a 5 watt here. If you check in the yesterday's numericals, we considered here it is equal to 1, right? So we need to consider it is equal to 5 here. So after that you will be getting this type of equation. Next we can find the roots of this equation, which is equal to minus b plus minus under root b square minus 4ac divided by 2a, right? And accordingly we can simplify, right? You will be getting the two gate current values. One will be the positive, second one will be the negative, right? Then acceptable value will be positive gate current, right? So that will be your 0.702, right? Okay. The final answer will be 6.92. 6.92. Please correct it. Next, now let us discuss the numericals related to the protection of SCR. Let us first read it. In the given figure, the source voltage is 100 volt and the load resistance is 10 ohm. Okay, source voltage Vs is 100 volt and the load resistance is 10 ohm. The SCR can withstand a dV by dt value of 50 volt per microsecond. So they have given maximum dV by dt. Our SCR can withstand a dV by dt value of 50 volt per microsecond. If the snubber discharge current must be limited to 2 ampere. Now snubber discharge current means what? The discharging current of the capacitor. Okay, and it is given that must be limited to 2 ampere. Find the value of snubber resistor and capacitor. Okay, so this numerical can be solved by two ways. One is by deriving the expressions and second one is the shortcut method. But for shortcut method, you need to be perfect in the network theory. Then and only then you can find the answer. Okay, we are going to discuss in both the ways how to simplify this numerical, right? So here our task is to find the value of snubber resistor and capacitor. Means our task is to find the value of R and C. Okay, so let us first note the data, right? Let us first note the given data. So here supply voltage Vs is given, it is equal to 100 volt. Load resistance RL, it is equal to 10 ohm. Next, maximum dV by dt, maximum dV by dt with which our SCR can withstand is equal to 50 volt per microsecond. This can be written as 50 upon 10 to the power minus 6 volt second. Okay, it is a microsecond, so I have written it as 50 upon 10 to the power minus 6. Okay, volt second. Next, if the snubber discharge current must be limited. Okay, so the snubber discharge current, right? Limit for snubber discharge current. Snubber discharge current is equal to 2 ampere, is equal to 2 ampere, right? And our task is to find the value of the snubber resistor, that is a R, and a snubber capacitor, that is a C, right? So now here snubber circuit is used to protect the SCR against high dV by dt, right? Why it is required to protect the SCR against high dV by dt? Yes, can anyone? Why we are required to protect the SCR against high dV by dt? In order to avoid, yes, false triggering, right? False triggering only, very good. So in order to avoid the false triggering, so snubber circuit is required to protect SCR against the false triggering. So false triggering means what? It is like we are not interested in turning on the SCR, but due to the high dU by dt, our SCR is turning on. Okay, so now can we say that while analyzing this snubber circuit, we need to consider that SCR is in a off state only? Because when SCR is in a off state, then and only then, yes, there will be the false triggering possibility. Na? If SCR is in a on state, whether the false triggering possibility will be there? No. Is this clear? So that's why keep it in mind, right? While finding the RC values, that is the snubber circuit parameter values, we need to consider SCR is in a off state only, right? SCR is in a off state only, right? So now when SCR is in a off state means it is like a open circuit. It is like a open circuit. So how this capacitor will be getting charged? Can anyone? Yes, suppose this SCR is in an off state. So current will flow from Vs, RL. This diode will be in the conduction mode now. And after that, the current will flow through the capacitor. So in this loop, the current will be flowing. Means our capacitor will go on charging. Yes or no? Our capacitor will go on charging. How the capacitor charges? Capacitor charging through the diode. Current flowing through the resistor R will be 0 because across resistor R it is like complete a short circuit branch. The diode is in the on state, na diode will be in the conduction mode. Okay, so let me draw here. Yes, when SCR is in off state, when SCR is in off state, yes, we can draw the circuit. This is a REL. SCR will be in the off state, right? Diode D will be in a conduction mode. The diode D will be in the short circuit, and this type of circuit will be getting. This is a VS. Okay. Here it is a REL. This is a diode D, and here it is a capacitor, right? So our capacitor go on charging. So to which voltage the capacitor will be getting charged? Yes. To which voltage this capacitor will be getting charged? Come on. This capacitor will be getting charged to the voltage of same as that of the supply voltage. Yes or no? Right? Capacitor will be getting charged to the voltage of supply voltage with a polarity upper plate positive, lower plate negative, because current is flowing like this, na? Right? And as we know, current always flows from point of higher potential to the point of lower potential. So definitely current direction in this capacitor, when capacitor charges, the direction of current in this capacitor will be in the downward direction. So downward means higher to lower. So plus here, minus here, this will be your capacitor voltage, which is equal to Vs, which is equal to Vs. Okay, Vc is equal to Vs, right? So to this voltage, the capacitor is charging. To this voltage, the capacitor is charging. Right? Okay. Next. So now, so capacitor will be charged to the voltage of, yes, Vs volt. Now, once thyristor turns, what is the purpose of this resistor in a snubber circuit? Yesterday we discussed. What is the function of this resistor in this snubber circuit? To limit the discharging current of the capacitor, na? Because we are having the capacitor. That capacitor will successfully oppose the dV by dt. But in order to limit the discharging current of the capacitor, yes, we require a resistor that should be connected in series with the capacitor, na? So that's the function of the resistor is to limit the discharging current of the capacitor, right? Now, how the capacitor will discharge? The capacitor will discharge when the thyristor will be in the on state. Yes or no? Please try to understand the circuit operation. Very first, what happened? We have considered the SCR is in an off state. When SCR is in an off state, our capacitor go on charging, and capacitor charges to the voltage of Vc is equal to Vs volt. Vc is equal to Vs volt, and the polarity is plus here and minus here. Upper plate positive, lower plate negative. Right? Similarly, next, when SCR is in an on state, when SCR is in an on state, it is like capacitor which yes, capacitor charged to polarity like upper plate positive, lower plate negative. Then when SCR turns on, our capacitor starts discharging in this loop, na? Okay. So they have given the upper limit for the discharging current. Limit for snubber discharge current is 2 ampere. They have given. So accordingly, we can find the value of resistor. Yes or no? We can find the value of resistor. So let us first find the value of resistor. Okay. So next, when SCR is in on state, when SCR is in on state, so circuit will be like this. So Vs, REL, SCR short circuit. Here it is a resistor, and here it is a charged capacitor. Charged capacitor, right? Now, so now what will happen? This capacitor, once SCR turns on, right? This capacitor will discharge. This capacitor will discharge. Let me write it as I dash. This I dash is discharging current of capacitor. Discharging current of capacitor, right? I dash is the discharging current of capacitor. Okay. So now, to which voltage capacitor is charged? Capacitor is charged to the voltage of Vs volt. So here voltage is Vs volt. So what is the maximum value of that discharging current? It is a Vs divided by R. Yes or no? Right? If capacitor has charged, suppose the capacitor is charged to the voltage of, let us consider 200 volt. And if we connect a resistor, na, because across capacitor we are having only resistor in this loop, right? So if we connect a resistor of 10 ohm, then how much maximum current will flow? It is a 200 divided by 10. So that is a 20 ampere. In this case, how much maximum discharging current will be flowing? That is equal to Vs divided by R, right? So therefore, maximum definitely here it is a Vs, here it is a RL. Okay, maximum discharging current of capacitor is equal to Vs divided by R. Is this very clear to all? Right? It is a Vs by R only. Now what is Vs? Whether they have given the Vs value, you can check. Vs is 100 volt, right? Vs is 100 volt and discharging current is 2 ampere. So you can write here 2 ampere, that is the maximum discharging current they have given, which is equal to 100 divided by R. So from this can we write, therefore R is equal to 100 by 2, that is equal to 50 ohm. Is this clear? Means in order to limit the discharging current to 2 ampere, we need to put a resistor of 50 ohm in the circuit, right? 50 ohm in series with the capacitor actually. Is this clear? So this is about the value of the snubber resistor. Now how to find the value of the snubber capacitor? How to find the value of snubber capacitor? That we need to think. Okay. So for finding the value of snubber capacitor, yes, when SCR is in an off state, then current will be flowing like this. Na? So consider this current is a capacitor current IC. Now we need to apply KVL to this loop. We need to apply KVL to this loop. And we need to find the expression for the IC. And after that, we can find the expression for VC accordingly. Right? So now let me write here. What happens if R is also there while charging? If R is also there while charging, then also capacitor will be getting charged to the same voltage. Okay. So next. Now, when SCR is in an on state, when SCR is in off state, whatever we draw on the circuit, SCR is in off state. So for that, let us redraw that circuit same. Vs here it is a RL, SCR off state, diode D on state, and here it is a capacitor that was charging. Na? So this capacitor was charging. This is a Vs, let me write it as a 100 volt directly. Here it is a RL value they have given. Yes, RL is equal to 10 ohm. 10 ohm. Here it is a SCR, diode D, and it is a capacitor. Okay, capacitor current, consider this as a IC, right? It is like capacitor charging. Whatever we discussed the theoretical operation before this. Okay, next, now can we apply KVL to this loop? Yes, KVL to loop. It is a plus 100 minus 10 into IC minus 1 by C integration of IC into dt is equal to 0, right? So now here we can write it as 100 is equal to 10 into IC plus 1 by C integration of IC into dt. Can we take the Laplace transform on both these sides? Yes, taking Laplace transform on both sides. So we can write it as 100 by S, which is equal to 10 into IC of S plus 1 by CS into IC of S. Okay. So 100 by S is equal to 10 into IC of S plus 1 by CS into IC of S. Okay. C we need to find, right? So therefore we can write, therefore this can be written as 100 by S is equal to 10 into CS, okay, plus 1 divided by CS into IC of S. Okay. So further we can write, therefore S will get cancel out. Okay. Now can we take 10 into C outside from this so that coefficient of S becomes equal to 1. So it is 100 is equal to 10 into C, okay, divided by this C as it is, into bracket S plus 1 by 10C, S plus 1 by 10C into IC of S. This CC will get cancel out. So therefore we can write IC of S is equal to 100 divided by 10 means it is a 10. Na? 10 divided by, this can be written as S plus 1 upon 10 C. Right? 100 divided by 10, that is a 10. And this term divided by to the left hand side. So it will be like a divided. Okay. So now can we take the inverse Laplace transform? Yes. So taking inverse Laplace transform. So we can write it as therefore IC is equal to 10 into e to the power minus t upon 10 into C. This is the expression for current flowing through the circuit. That is the IC, capacitor current. Now can we derive the expression for VC, voltage across capacitor? Okay, because they have given the maximum dV by dt now, right? So can we write the VC expression? Yes. So now dV by, yes, VC. Before that, let me write VC, voltage across capacitor. Voltage across capacitor. Yes, VC is equal to 1 by C integration of IC into dt. Capacitor charging, so limit should be 0 to t, right? So let me write it as therefore VC is equal to 1 by C integration over 0 to t. This IC can be replaced with 10 into e to the power minus t upon 10 into C into dt, right? Can we take this 10 outside constant? Okay, so it will therefore VC is equal to 10 upon C into integration of e to the power minus t by 10 C. So it is e to the power minus t upon 10 C, right? Divided by minus 1 upon 10 C, right? So this will be like this, the integrate limit 0 to t, right? So therefore we can write VC is equal to, you can check this 10 by C, and this is we can write this as 10 by C, and this will be like a 10 C, na? Right? So C will get actually cancel out, so it is like 100. Are you getting the point? This C and this C will get cancel out, and this 1 divided by 10, na? So that 10 will go in the numerator, so 10 into 10, that will be 100 into, if we put the limit, that will be like e to the power minus t upon 10 C, minus will be here as it is, plus e to the power 0. E to the power 0 means 1. So therefore VC is equal to 100 into 1 minus e to the power minus t upon 10 into C. This is your voltage across capacitor. Voltage across capacitor. Now, can we find the dVc by dt? dVc by dt, right? Because they have given the dV by dt, na? Right? So therefore, let me write now d by dt of Vc, that is a dVc by dt, which is equal to d by dt of this term, 100 into 1 minus e to the power minus t upon 10 C. So this can be written as is equal to, yes, we can write it as a, take 100 outside, 100 into integration of 1 is, sorry, differentiation of 1 is 0. So it is a 0 minus differentiation of this term. So it is like a e to the power minus t upon 10 into C into, yes, minus 1 upon 10 into C. Is this clear? This is a differentiation. Huh? So that's why we want to multiply here, right? So this minus, it will become plus. So therefore, dVc by dt is equal to 100 divided by, let me write it as a 10 C into, this can be written as e to the power minus t upon 10 into C, right? This will be, therefore dVc by dt is equal to 10 upon C, right? Into e to the power minus t upon 10 C. This is a dVc by dt. Now, here, if you check in the circuit, when SCR is in an off state, right? When SCR is in an off state, it is like an anode of the SCR. Here it is a cathode of the SCR. So what is the voltage across SCR? That is a plus here, minus here. This is the VT, na? Voltage across SCR. So when SCR is in off state, can we say that this VT is nothing but voltage across capacitor only, because you can check this resistor and this capacitor, these are connected in parallel na, right? Because current is flowing through the diode. So that's why capacitor voltage is nothing but your VT, voltage across resistor, right? So dVc by dt is nothing but your same dVt by dt only. Rate of change of voltage across capacitor is equal to rate of change of voltage across resistor. Is this clear? Right? So therefore we can write now this dVc by dt will be maximum when t is equal to 0. You can check if t is equal to 0. If t is equal to 0, this term will become equal to 1 na? So that's why the dVc by dt will be 10 by c. If t goes on increasing, if time go on increasing, it will be like e to the power minus of that time. Suppose t is infinity plus infinity, so it is e to the power minus infinity will be there na, because minus is here, right? So e to the power minus infinity will be 0 na, right? So dVc by dt will be maximum when t is equal to 0. Okay, let me write. So at t is equal to 0, dVc by dt, yes, will be maximum. So therefore we can write maximum dVc by dt, right, which is equal to dVc by dt at t is equal to 0, at t is equal to 0, which is equal to 10 by c into e to the power minus 0 by 10c. So it is the power 0 only. So that will be equal to your 10 by c. Yes or no? Right? So that will be equal to your 10 by c. Next, so what is the maximum dVc by dt? Whether they have given? Yes, it is a 50 volt per microsecond. They have given, right? So can we write it as 50 volt per microsecond means 50 divided by 10 to the power minus 6 volt per second, which is equal to 10 upon c. Now from this, can we find c? So therefore c is equal to, you can write 10 into 10 to the power minus 6 divided by 50. So which is equal to 0.2 microfarad, right? 1 by 5 microfarad. So that is a 0.2 microfarad. Is this clear? This is the one way to find the R and C values, right? R and C values. Okay, but here we need to derive the expressions. Right? And then and only then we can find what is the value of C. R value is very easy. Finding the value of current discharging current limiting resistor is very easy, right? Because we need to think only what is the maximum value of the voltage across capacitor. That is nothing but the voltage to which the capacitor will be getting charged. And again, we need to check that voltage divided by the resistor. That will be equal to your discharging current, maximum discharging current. Is this clear? So C is equal to 0.2 microfarad here. Next, let us discuss the second method. Okay, so second method here. Yes, this type of questions they have asked before this. Okay. Yes. Right. Next. So now let us discuss the second method. Yes. So for the second method, let me redraw the network again. We are having the Vs here. That is 100 volt now. Next here it is a RL 10 ohm resistor no. Next here it is a thyristor. Here it is a R. Here it is a capacitor C and a diode. Right? This is a C. This is a R and a diode. Our task is to find the R and C. Right? The resistor value we can find in the same way. Right? Resistor value we can find in the same way. Okay. So how to find the resistor value? First of all, we need to check the maximum voltage across the capacitor. Okay. So VC will be equal to 100 volt. This is the value of voltage at which your capacitor will be getting charged with a polarity plus here and minus here. So this is your Vs, which is equal to 100 volt. Next, the discharging current of the capacitor will be like when SCR turns on now, the discharging current is equal to this 100 divided by R. Okay. So discharging current means whatever we discussed, the same discharging current of capacitor is equal to, it is a Vc divided by R, right? So same way we can find it is a 2 ampere is equal to 100 divided by R. So therefore R is equal to 100 by 2, which is equal to 50 ohm. Means whatever we discussed in the first method, in the same way we need to find the resistor of value of the resistor R. Now how to find the value of capacitor? Okay, that is important because you can check in the previous first method also for finding the expression of the current flowing through the capacitor, and it's again differentiation. Okay, that takes a time, right? So that's why the time for solving this numerical, right, it was a very high. Now let us check with the help of network theory how to simplify this, okay, for finding the value of capacitor, right? So let us check here. They have given maximum dV by dt, okay. So maximum dV by dt they have given, it is a 50 upon 10 to the power minus 6 volt per second. Now you can check in the case of capacitor. In case of capacitor, yes, whether we are having the expression IC is equal to C into dVc by dt. For any capacitor, we can write this expression now. Current flowing through capacitor is equal to C into dVc by dt, right? Now, if you check, can we replace this dVc by dt with a maximum dVc by dt? Yes, but at the same time, we need to replace this IC with maximum IC na. If I replace this dVc by dt with a maximum dVc by dt, then I need to replace this IC with a maximum IC, yes or no, right? So same I can write maximum IC. Maximum IC is equal to C into maximum of dVc by dt. dVc by dt. Out of this maximum dVc by dt they have given, right? We know this value. The thing is, we need to find the maximum IC value. We need to find the maximum IC value. Once we get the maximum IC value, definitely we can get the value of capacitor. But how to get that value of maximum IC, that we need to think. Okay, now you can check here in this circuit. In this circuit, when thyristor is in an off state, it is like our capacitor go on charging. Okay, but when thyristor is in an off state, suppose that T is equal to 0. Yes, it is like our capacitor starts charging. At T is equal to 0, our capacitor starts charging. The meaning is before T is equal to 0, it was like our capacitor voltage was 0 na, right? So at T is equal to 0, what will happen? Our capacitor will oppose the sudden change in the voltage. So at T is equal to 0, capacitor will act as a short circuit, yes or no, right? So if capacitor acts as a short circuit, in that case, the current flowing through the capacitor will be your maximum current na. You can check here. Once capacitor starts charging means what? Voltage across capacitor go on increasing. If voltage across capacitor increases, current flowing through the capacitor decreases na. You can recall the voltage and current waveforms of the capacitor during charging. During charging, capacitor voltage increases, but what about the capacitor current? It decreases na. So maximum current flows through the capacitor only at the instant of, or you can say only at the transient or the switching instant, at the switching instant, right? So let me write here. Yes, at T is equal to 0. At T is equal to 0. Yes, we can draw the circuit like it is a Vs. This concept is having a base of transient response from network theory. If you are perfect in that network theory transient response, then and only then go for this method. So at T is equal to 0, your capacitor will act as a short circuit now. This is a 100 volt. This is a 10 ohm. This is a diode D, and this is a capacitor which is acting as a short circuit. At T is equal to 0, capacitor will act as a short circuit, because before that the capacitor was uncharged, right? So as soon as t is equal to 0, the excitation is applied, our capacitor will behave as a short circuit in order to maintain the same voltage. So now when here voltage is 0, then and only then this current will be maximum. Na? You can check, instead of this 0 volt, you can consider 10 volt. You will understand this capacitor will oppose the charging. Na? Once capacitor starts charging, you can check here. Suppose we are having a resistor here, for example, and let us consider a voltage source here. Let me put a switch also. Let me put a switch also here. Suppose the switch is here. Right? Suppose this switch is there. So suppose this voltage is a 5 volt. Let me write it as a 2 ohm, and here it is a capacitor we are having. Now initially this capacitor is uncharged. Okay, so at t is equal to 0, when this switch is closed, at t is equal to 0, when this switch is closed, so as soon as this capacitor will act as a short circuit. So when capacitor acts as a short circuit, this current, let us consider it as a IC. So at t is equal to 0, what is the current in the capacitor? IC is equal to, it is like 5 by 2, na? 5 by 2, so it is a 2.5 ampere. Now once the capacitor starts charging, suppose capacitor voltage is now 1 volt. Suppose capacitor voltage is now 1 volt, means from 0 volt it has started 1 volt. Okay, it has started charging, and now its voltage is, it has charged to the voltage of 1 volt. So if this voltage is 1 volt, whether the current IC will remain 2.5 or it will be less than 2.5? That yes, the current will be less than 2.5. Now simply apply KVL, you will understand. What is IC now? IC is equal to 5 minus 1 divided by this 2, na? So it is equal to 4 by 2, so it is a 2 ampere. Once this capacitor will be charged to the 2 volt, this current will further decrease. When capacitor voltage increases to 3 volt, 4 volt, and maximum voltage will be 5 volt. Na? So when capacitor voltage equals to 5 volt, it is like here it is 5 volt, here it is also 5 volt. So resultant current will be 0. So always keep it in mind. When capacitor charges to the maximum voltage, that is at steady state, generally we say na, in transient response or in the transient theory, we are having the statement like in steady state, capacitor acts as an open circuit. So capacitor acts as open circuit means what? It is like capacitor will be getting charged to the maximum possible voltage. That is nothing but the open circuit. The meaning is there. Okay. So here maximum current is flowing only at the t is equal to 0. Right. So now here can we write IC max? So therefore here, therefore IC is equal to IC max is equal to how much? You can apply KVL to this loop. Na? What is the IC here? 100 by 10. 100 by 10. So it is equal to 10 ampere. This is the IC max. Now we are having IC max is equal to C into maximum value of dVc by dt. Na? Again, I am repeating, voltage across capacitor is same as that of the voltage across thyristor, right? Because these two are connected in parallel. Na? So whatever the rate of change of voltage withstanding capacity of the thyristor is given, the same dVc by dt will be there for capacitor applicable. Okay. So this is a 10, which is equal to C into 50 upon 10 to the power minus 6. Okay. So accordingly, we can find C. C is equal to 0.2 microfarad. Is this clear? Yes. Do you want to say something, Uma Maheshwari and Moka Baby Kavi? You have raised the hands. Yes, Bala. No, no. Okay. Okay. Yes. Right. Is this clear? So this is the second way. Here, what we need to do? We need to check the maximum capacitor current, and this is a yes normal expression. IC is equal to C into dVc by dt. For any capacitor, this expression is valid. So if dVc by dt is maximum, your IC will be maximum. So we need to find the maximum IC only. Once you find the maximum IC, you can get the capacitor value, right? So this is the second method. Next, let us discuss the next example. A thyristor is placed between a constant DC voltage source of 240 volt and a resistive load RL. The specified limits of di by dt and dv by dt for SCR R 60 ampere per microsecond and 300 volt per microsecond respectively. So di by dt they have given and du by dt they have given. Determine the values of di by dt inductor and snubber circuit parameters. Take a damping ratio as 0.5, means zeta value they have given, right? So it is not a straightforward question. This question is a design question actually, right? So because here they have added the inductor also. Whatever the numerical we discussed just now, in that numerical only R and C were there. Okay. But now here, yes, we are having the inductor also. We are having the inductor also. So determine the values of di by dt inductor and a snubber circuit parameters. Means we need to find L, we need to find R, we need to find the C. Right. So let me draw the circuit first. It is given source voltage is equal to 240 volt. The specified limits, that is a maximum di by dt is equal to 60 divided by 10 to the power minus 6 ampere per second. Maximum dv by dt is equal to 300 divided by 10 to the power minus 6 volt per second. Okay. So our task is to find L, R and C, right? We need to find these values. So now yes, let me draw the circuit diagram first. We're having the supply voltage Vs, that is a 240 volt. Let me write it as a Vs only here. Load resistor RL, okay. Inductor di by dt inductor. Next SCR we are having, okay, and across SCR we are having the RC snubber circuit. So this Vs here it is a RL, this is a L, R or RS you can write CS. RS means snubber resistor, CS means snubber capacitor. Okay, snubber resistor and snubber capacitor. This is a snubber circuit, na RC circuit. And here we are having the inductor. Here we are having the inductor. Now our task is to find the L value, R value and C value. Okay, let us consider voltage across thyristor is a VT. Voltage across thyristor is a VT, right? Next. So now first important thing here, what is the function of the di by dt inductor here? What is the function of this inductor? To oppose the change in current, right? That is nothing but to protect the SCR against the high di by dt, na? To protect SCR against high di by dt. Now here in this case, whether this CS will oppose the rate of change of current. Please check my question. Please listen it carefully. Whether this CS will oppose the change in the current, or due to the CS, whether the current in the circuit, okay, will be changing or it will be independent of the CS. Can anyone? You can check the circuit operation. Independent. Most of the saying are independent. Someone is saying change. Okay. Let us discuss. So what is happening actually in the circuit? Suppose when SCR is in a off state, so let me write when SCR is in a off state, okay. So at that time the circuit will be like this. RS, CS, right? So this type of circuit we are having. This is a VS. Let me write it as a VS. This is a RL, L, and here it is a RS, and here CS. Okay. So when SCR is in an off state, that is this voltage will be your VT. Okay, voltage will be your VT. Now you can check here. when SR is in a off state, when SR is in a off state, it is like a capacitor go on charging. Okay, capacitor go on charging. So whether the charging of the capacitor, suppose the initially capacitor is uncharged na, so definitely at t is equal to 0, your capacitor will act as a short circuit. After that, capacitor go on charging. Capacitor charges means the polarity will be plus here and minus here. Here it is plus, here it is minus. Okay, so once capacitor go on charging, whether this capacitor will oppose, whether this capacitor will oppose whatever the current that is flowing through this branch, definitely please keep it in mind. Okay, because when capacitor starts charging means what, means some voltage is appearing across the capacitor na. So when capacitor goes on charging, okay, so at that time this capacitor will oppose then whatever the current that will be flowing through this branch. Okay, so that's why here, in order to find the value of the di by dt inductor, we need to consider that value should be independent of the capacitor, right? Means we need to find, because this is like a design problem. Means here once we cannot find the value of the inductor, right, by considering this capacitor, because here what is happening, this capacitor is also opposing the change in the current. How the capacitor is opposing the change in the current, you can check. Once capacitor starts charging means here it is plus, here it is minus. Okay, same thing we discussed here, you can check here, right? In this previous case we discussed, in this previous numerical we discussed the same thing. Yes, yes, here once capacitor starts charging, it is like what will happen, plus here minus here, so this voltage will indirectly oppose this whatever the charges na, those will be coming here on this plate of the capacitor or as well as this plate of the capacitor. So indirectly your capacitor will oppose the change in the current. So please be careful, capacitor will oppose the current, actually capacitor will oppose the current, right? So that's why while calculating this inductor value, we need to remove this capacitor. Okay, we need to remove this capacitor. This is a standard procedure for finding the value of L, right? We need to consider the worst case condition, just like we need to remove this capacitor, we need to remove this capacitor, right? So now, so for finding L, for finding L, yes, remove CS, we need to remove CS, right? So now if we remove CS, then what will happen, it will be like circuit will be like this, VS RL, here it is a thyristor which is in an off state, inductor is there, right? So one inductor is there, here it is a RS and here it is a capacitor. Okay, and this type of circuit will be getting, I have removed this capacitor and I have connected there a short circuit. This is a VS, this is a RL, here it is a L, this is a RS, and here it is CS was there but we have removed it. Okay, and this voltage is a VT, this voltage is a VT, voltage across thyristor. Now next, now can we apply KVL to this loop? We can apply the KVL to the loop, right? So let me write current here is IL, right? Consider current here is IL. Okay, so KVL to loop, KVL to loop. So therefore it is a plus VS minus RL into IL minus L into DIL by dt minus RS into IL is equal to 0, right? So this can be written as, therefore VS is equal to L into DIL by dt, okay, plus RS plus RL into IL. Okay, so this is the differential equation we are having, that is like a RL circuit. Now we are having only RL here and here it is a RS and here it is an inductor, so it is like a resistor plus inductor circuit. Okay, so by taking the Laplace transform and after simplification we can write expression IL. I'm writing it directly, but you can take the Laplace transform here and again simplify it. Okay, till IL. So IL will be getting, it is equal to, yes, it is a Vs divided by Rs plus RL. That is a steady state current into 1 minus e to the power minus t by tau, na, e to the power minus t by tau. So it is like a minus t upon tau. Tau is nothing but L by R. So it is like a L, okay, divided by R is nothing but that will be into Rs plus RL. Rs plus RL. Is this clear? So this is the final expression of current IL, Vs by Rs plus RL. That is the steady state current. You can check in this circuit. At steady state, your inductor will act as a short circuit, na? Right? So inductor go on storing the energy in its magnetic field, and at steady state, it will behave as a short circuit. So what is the steady state current? Vs upon Rs plus RL. So this is a steady state current. Into 1 minus e to the power minus t upon this, t by tau actually. Tau is nothing but L by R. So this is the L, and here it is Rs plus RL. That L by divided by L upon Rs plus RL will be there, but that L upon that term, that term will go here, right? Rs plus RL. Next, so this is the IL expression. Now can we write the DIL by dt? Yes. So therefore DIL by dt is equal to d by dt of, yes, this term. It is a Vs upon Rs plus RL into, let me write as 1 minus e to the power minus t into Rs plus RL divided by L. Okay. So now we need to differentiate this term. So therefore DIL by dt is equal to Vs upon Rs plus RL. This is a constant, so as it is I have taken, into what is the differentiation of 1, that will be 0, minus differentiation of this term e to the power minus t into Rs plus RL upon L. Okay, into here it will be again differentiation of this term, so it is like minus of Rs plus RL divided by L, na? Right? So this minus it will become plus. Okay, and here it is this Rs plus RL, this Rs plus RL, it will get cancelled out. So therefore DIL by dt is equal to Vs upon this L. I'm writing it as a L. This L I have taken outside, na? So Vs by L into that will be e to the power, this minus it will become plus, right? So e to the power minus of t into Rs plus RL divided by L, right? E to the power minus t into Rs plus RL divided by L, right? Now this is the DIL by dt. Now you can check this DIL by dt is exponential decreasing, na? So at what time this DIL by dt will be maximum? At t is equal to 0, right? So at t is equal to 0, DIL by dt will be maximum. This DIL by dt will be maximum, right? Because you can put here from 0, you can put some finite value, you can check for infinite value. At t is equal to minus infinity, it will be 0, na? Because here minus is there and t is equal to infinity, e to the power minus infinity, that will be 0. Okay, so therefore we can write maximum DIL by dt is equal to DIL by dt at t is equal to 0, which is equal to, we can write it as Vs upon L into e to the power 0, na? So therefore maximum DIL by dt is equal to Vs by L. So from this can we write L is equal to Vs upon maximum of DIL by dt. Maximum DIL by dt. Either you can simplify like this or you can simply memorize this expression. From this expression you can get the value of L, right? Because they have given DIL by dt, na, maximum value. So we can find the value of L, right? So let me write here. Therefore L is equal to, what is Vs value they have given? Vs is equal to, let me check, 240. Okay, and maximum DI by dt is equal to your 60 divided by 10 to the power minus 6. Okay, so it is equal to 240 divided by 60 upon 10 to the power minus 6. So that will be equal to your 4 microhenry L. Okay, so it is a 4 microhenry. This is your inductor L value, 4 microhenry, right? Now can we find the can we write further? You can check this circuit here. In this circuit, can we write Vt is equal to Rs into IL, right? Vt means voltage across thyristor, which is equal to voltage across resistor, na? Means between these 2 points, whatever the voltage here, the same voltage will be across the Rs. So we can write Vt is equal to Rs into IL. Okay, Vt is equal to Rs into IL. Also, Vt is equal to Rs into RL.
Hello, sir.
Do you want to say something?
Yes, sir. So in question it is given determine the values of di by dt inductor. What does that mean, sir?
Yeah, just a bit. I will let you know. Di by dt inductor means your L value only.
Okay, okay, sir.
The same thing now we have calculated.
Yes, sir.
Di by dt inductor means the function of L is to oppose the di by dt, na?
Yes, sir.
To protect the thyristor against di by dt. So that's why they have given di by dt inductor, right?
Okay, okay. We should find out the L value. That's
Only, yes,
inductance value.
only L value and the snubber parameters, that is R and C.
Yes, sir. Okay.
Next, Vt is equal to, we can write it as a IL into Rs. So further we can write differentiating both the sides. Okay, differentiating both sides with respect to t. So therefore it is like a dv by dt or dvt by dt you can write. Okay, is equal to dil by dt into Rs. Yes or no? So further can I write it as, if dil by dt is maximum, definitely this term will be maximum. Okay, so therefore maximum of dvt by dt is equal to maximum dil by dt into Rs. So from this can we write Rs? So therefore Rs is equal to maximum dvt by dt. They have given the maximum dvt by dt, right? Divided by maximum dil by dt. So what is the maximum dvt by dt? They have given, it is equal to, you can check here. Yes, 300 divided by 10 to the power minus 6, and this is a 60 upon 10 to the power minus 6. Okay, 300 upon 10 to the power minus 6 divided by 60 upon 10 to the power minus 6. So 10 to the power minus 6, 10 to the power minus 6 cancel out. So therefore Res, you can check here, Res is equal to 5 ohm, right? 300 divided by 60, that is a 5 ohm. Is this clear? So this is the value of required resistance Res. Either you can simply, yes, memorize this expression, or you can simplify like this. Okay, now, so this is the expression for the Res. We have already written the expression for the inductor also, right? Next, they have given the value of zeta also. Okay, but from the control system, if you check where, if we are in the RLC circuit, now in order to find the capacitor, definitely we need to consider the capacitor in the circuit. Now we will be having the circuit like RLC, that is a second order differential equation you will be getting after applying the KVL. Okay, and if we compare that equation, okay, with your control system, then whatever the equation of zeta you are having in control system, same zeta you can use here. Okay, so what is zeta? Zeta is equal to R by 2 under root C by L. This expression is directly available for a second order differential equation. Or we can draw the equivalent circuit, okay, by considering the capacitor also in the circuit, right? And then we need to apply KVL, we need to take the Laplace transform, and after that you will be getting the equation in terms of S square. Okay, yes, and as well next one is the constant. So in this way also we can find, but I'm directly using the expression zeta is equal to R by 2 under root C by L. What is the zeta? They have given it is a 0.5 is equal to R. R is nothing but it is a 5 ohm, right? In our case. Okay, so it is a 5 by 2 into under root C by L. C is like capacitor. We need to find the capacitor value divided by L. L value we have calculated is a 4 microhenry. 4 into 10 to the power minus 6, right? So from this we can simplify and we can find the value of capacitor. Therefore C is equal to, yes, what is the C here? We'll be having circuit like this. RL, right? Here it is a L. Here we're having a RES. Here it is a CS. Okay. So this type of circuit we'll be having. This is a BS, RL. This is a L, RES and CS. Just a minute. Instead of R here, we need to put here RES plus RL. RES plus RL in our case. Okay. So RES plus RL we need to put. Because we are having the two resistors. No? In our circuit, it is a two resistors. So what is the RL? I think it is a 10. Na? So that's why it will be 15. Please check what is the C or CS. (0.16 microfarad, right? Is this clear? Okay. So if RL is okay. RL value they have not given. Okay, simply neglect it. Simply neglect it. Okay, we can write directly. Then it is a 5 only. We can write 5 only, right? Is this clear? So it is a 0.16 microfarad. Now, if you check here, two types of questions they may ask regarding the protection of the SCR. One is either based on your snubber circuit only, that is the RL, RES and CS. And second is by considering the di by dt inductor also. So if di by dt inductor is present, then in that case, okay, then in that case, simply either you need to simplify like this way, or you can simply memorize these two expressions, right? One is this zeta expression, right? Second one is this yes, RES expression. It is very simple, maximum of dVt by dt upon maximum of dIL by dt. And third expression is this one. For finding the value of EL, whatever we have written. Yes, this is expression. Okay, Vs upon maximum of dIL by dt. Is this clear? Right? So either you can memorize these expressions or simple like this. For finding L, we are considering only L. We are not considering CS because we need to find. Suppose a manufacturer has designed one device, that is the SCR, right? Now, in the SCR, in order to protect the SCR against the di by dt, we need to design a value of the inductor. Okay, so that value of the inductor should be designed in such a way that by considering the worst case condition, I am saying worst case condition means whatever the value of di by dt will be there, okay, in the circuit, the our inductor should successfully, right, limit that di by dt, because you can check this numerical. They have given the maximum di by dt and the maximum du by dt for the thyristor, na? So what is the function of our inductor? Our inductor's function is to limit the di by dt, okay, in the circuit, right, to the value of that can be or the withstanding capacity of your thyristor. Means our inductor should not allow the di by dt to be greater than whatever the di by dt of your thyristor. Similarly, the function of the capacitor is to limit the dV by dt. Okay, and what should be the limit for the dV by dt? The limit for dV by dt is nothing but the dV by dt rating or the capacity of our thyristor. In the numerical, they have given di by dt value of the thyristor, okay, and dv by dt value of the thyristor, right? So our function of these two elements L and C, okay, is to limit those dv by dt and di by dt, so that our thyristor may either the false triggering will be avoided or the permanent damage will be avoided. In the case of di by dt, we are having the permanent damage due to the hotspot, local hotspot creation, right? And in the second case, we are having the false triggering, right? Okay. So next, why we consider SCR initially open? Because the false triggering meaning is SCR is in off state only, na. False triggering means what? SCR is turning on. We are not interested in turning it on, but it is turning on. When the SCR will false trigger, before that it should be in the off state, na. So that's why we need to consider the off state only, right? Next, so this is about the numericals related to the protection of the SCR. Now let us discuss the series parallel operation of SCR, right? Next concept, series parallel operation of SCR. So before that, let us first discuss why the series connection of SCRs is required, SCRs are required, and why the parallel connection of SCRs are required. Okay, so let us put the heading series connection of SCR. Series connection of SCR. So my question is, why it is required to connect the SCRs in series? Yes, can anyone? Why it is required to connect the SCRs in series? Come on. Yes. Suppose we are having more current. For more current, the series connection is required. No. Please listen. Please listen. For example, suppose we are having a supply voltage. Let us consider it is a 500 volt. Okay. And here we are having a load, and the load voltage rating is also equal to 500 volt. Load voltage rating is 500 volt. Supply voltage is 500 volt. It is a DC. And suppose we are having a SCRs which are having a voltage blocking capacity of, let us consider 250 volt. Okay, 250 volt. So suppose if I connect a single SCR here, if I connect a single SCR here, right? If I connect a single SCR here, this SCR is having a voltage blocking capacity of 250 volt, right? 250 volt. Let me write it as a VT. It is having a voltage blocking capacity. I am saying voltage blocking capacity. The meaning is how much maximum voltage this SCR can block. It is a 250 volt, right? Now suppose here we are having a load, here we are having a supply, 500 volt supply, and load is also having a voltage rating of 500 volt. Okay. Now for our application, suppose for first 5 seconds, let me write it as a 5 seconds. Okay. And next here, let us consider 10 seconds and like this. Okay. So we're having a cycle like 15 seconds. Suppose a simple operation we're discussing. For the first 5 seconds, we require to turn on the load, or to connect the source to the load. Okay. Means indirectly what? Here, this will be the on time of the switch. Yes or no? Please listen it carefully what I am saying. For first 5 seconds, for a particular application, it is required that for the first 5 seconds, okay, it is required to energize the load. Energize the load means what? Whatever the supply is here, the full supply will be connected. Okay, should be connected to the load. That is nothing but the load is energized. Suppose next for next 5 seconds, okay, it is like a supply is required to be disconnected from the source, right? So that's why this switch should be in the off state. Again for the next 5 seconds, again it is required to connect the source to the load, means again to energize the load. Okay, so now here you can check, if we want to energize the load during 0 to 5 seconds, if we want to energize the load, definitely this switch should be in the on state, right? So definitely, suppose this switch is having a 250 volt voltage rating also, and if this switch is turned on, doesn't matter, our switch will successfully turn on. But the problem is you can check from 5 volt to 10, from 5 second to 10 second. What is our requirement? It is required that this source should be disconnected from the supply. Okay, so here let me write it as a de-energize the load. This is the energize the load. Okay, so de-energize the load means what? Yes, we are required to disconnect this source from the load. Now you can check here, in order to disconnect the load, in order to disconnect the source from the load, this switch should be in the off state. Now you can check here, when this switch is in an off state, what is the potential difference between these 2 points? It is equal to, you can simply apply KVL here. Okay, suppose we are having a load is like a resistive, for example, consider. Okay, and suppose current is not flowing now when switch is in off state, so current in the circuit will be 0. If the current in the circuit is 0, whatever the voltage across the load, definitely this voltage will be 0, right? So can we say that whatever the voltage here, this full voltage will appear across the switch, and our switch is in an off state now. So 500 volt is appearing across our SCR, but SCR is having a voltage blocking capacity of 250 volt. So what will happen? Whether our SCR will get damaged? Definitely our SCR will get damaged. Are you getting the point? Right? So that's why here we need to connect one more SCR in series. Right? Then and only then it is possible. So suppose if I connect one more SCR here, and this SCR is also having, let us consider the 250 volt. Vt is equal to 250 volt. That is the voltage rating or the voltage blocking capacity of this SCR. Now you can check when load is required to be de-energized. Okay, means source is disconnected from the load. Then at that time, both the SCRs should be in the off state. So when both the SCRs are in an off state, then can we say that yes, whatever the voltage across the, whatever the voltage here, that is a 500 volt, that voltage will be successfully blocked by these two devices? Yes, because this can block a 250 volt, this can block a 250 volt, right? So all together our two SCRs can block a 500 volt voltage. But instead of two SCRs, suppose if only single SCR is connected, and if that SCR is not having the voltage blocking capacity which is equal to the source voltage, then our SCR will get damaged. Is this clear? Are you getting the point? Okay, so that's why we need to connect the SCRs in series. We have the over voltage protection. Over voltage protection you have, but over voltage protection that only protect the SCR, na? But whether that will successfully block this 500 volt, no. Are you getting the point? Protection devices or the protection elements, their purpose is only to protect the SCR. If I want to block this 500 volt, na, then definitely yes, we need to connect the number of SCRs in series. Now suppose instead of 500, suppose we are having the, let us consider 1000 volt. Then what is happening? Then here we need to connect the two more SCRs. That is a total 4 SCRs. Okay, so please keep it in mind. If the voltage rating of the load, okay, or the system working voltage, generally we say, okay, if the system working voltage is greater than voltage blocking capacity or the voltage rating of a single SCR, then we need to connect the number of SCRs in series. Then we need to connect the number of SCRs in series. Okay, so let me write. If system means, now in this case this is a system. Okay, working voltage is greater than yes, voltage rating of single SCR, then we need to connect number of SCRs in series. Is this clear? We need to connect the number of SCRs in series, right? So this is the purpose of series connection, right? Now in the series connection, yes, we are having two terms. One is a string efficiency and second one is a derating factor. Okay, string efficiency and derating factor. So let us discuss the string efficiency. String efficiency. Yes. Suppose we are having the n number of SCRs connected in series. For example, suppose we are having the n number of SCRs connected in series. Okay, so it is like suppose T1, T2 dot 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 Tn. Okay, T1, T2 dot 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 Tn. Okay, so this is the, we are having the n number of SCRs connected in series. Okay, so let us consider the voltage rating of each SCR is a Vt. Okay, voltage rating of each SCR is a Vt, and whatever the voltage across this full series combination is nothing but your string voltage. This voltage is nothing but a string voltage. String voltage. Let us consider this voltage as a Vs. Okay, let us consider it as a voltage as a Vs, or let me write it as a V string, right? V string or a Vs. Now the string efficiency, definitely at this side we will be having a supply and at this side we will be having a load, right? I have shown only the n thyristors connected in series, right? So definitely at this side we will be having the source and the load, remaining things. Okay, next, string efficiency. String efficiency, yes, it is equal to, this can be defined as, it is equal to string voltage divided by number of SCRs connected in series. Number of SCRs connected in series. Okay, into voltage rating of each SCR, into voltage rating of each SCR, into 100. If you do, that will be your percentage string efficiency. Okay, so this is the important expression. Now you can check here, in this case the string voltage is V string, number of SCRs are n, into what, voltage rating of each SCR. Okay, voltage rating of each SCR. Generally the string efficiency is less than 100%. Why it is less than 100%, we are going to discuss. Okay, in the problems associated with the series connection of SCRs, you will understand why the efficiency is less than 100%. Okay, next, now string efficiency is less than 100%. One more factor we are having, one more parameter we are having related to this series connection, that is a derating factor. Derating factor, which is equal to 1 minus string efficiency. Derating factor is equal to 1 minus string efficiency. This string efficiency is in fraction, it is not in percentage. Here we have calculated in percentage, but while doing this 1 minus, we need to put it in fraction. If 98%, then that will be like 98 by 100. Okay, like this. So this is a derating factor, right? So these two terms, please memorize it. They have asked, sometimes they have asked in the state level PSUs, okay, or in the previous or the old gate papers also, right? They have asked the questions related to the string efficiency and derating factor. Now let us discuss the problems associated with the series connection of SCRs. This is very important. Problems associated with the series connection of SCR, right? So suppose we are having two SCRs connected in series. For example, suppose we are having two SCRs connected in series. So let me write here SCR1, SCR2. Suppose this is a T1, this is a T2. We have selected the two SCRs which are having the same voltage rating. We have selected the two SCRs which are having the same voltage rating. Okay, so next, So now in this case, these two are connected in series. Suppose the static VI characteristics of the SCRs are like this. This is a voltage across SCR. Let me write it as a VA, and current flowing through the SCR, that is a IA. Static VI characteristics of the two SCRs I am drawing. This is for the first SCR, let us consider. And suppose the static VI characteristic of the second SCR, it is like this. Both the SCRs are having the same voltage blocking capacity. Okay, suppose the green one is for the first SCR and this one is for second SCR. Okay, so we're having the two SCRs, both are having the same voltage blocking capacity. Okay, let me write it as a VBO. Both are having the same voltage blocking capacity, right? These two SCRs we have connected in series. We have connected in series because as long as the series connection of SCRs is considered, what generally we do? We select the SCRs based on their voltage rating and the current carrying capacity. Yes or no, right? So here what we are observing, actually the thing is, even though the two SCRs are having the same voltage blocking capacity, but they are not having exact, or you can say the identical static VI characteristic. You can check there is a difference between the static VI characteristics. Both are having the same voltage blocking, VBO, same voltage breakover, okay, capacity. But both are having their static VI characteristics are not exact same. Okay, right? Similar they are, but they are not exact same. Now the static VI characteristics is actually depends on, again, whatever the device properties you are having, whatever the doping level you are having, and those things. Okay, accordingly it varies slightly. Now these two devices we have connected in series. So what will happen if you check? Devices are required to connect in series. Why? Because in order to improve the voltage blocking capacity of the overall series connection, we have discussed now, because overall string voltage is greater than the voltage blocking capacity or the voltage rating of the single SCR, right? So voltage blocking we need to discuss means what? We need to focus on which mode of operation, that is a forward blocking mode of operation. Are you getting the point? For series connection, right? Suppose these two SCRs are in an off state. First SCR is blocking some voltage, second SCR is blocking some voltage. Why these two SCRs are blocking? The unequal voltages we are going to discuss. Okay, so blocking means what? They are in an off state. So off state means we need to consider what? This now blocking state. We need to consider the blocking state, right? So now let us consider, as these two SCRs are connected in series. So in the series connection, in the series circuit, whether the current will be same or different. When these two SCRs are connected in series, suppose both are operating in an off state, ideally speaking, the current should be zero. But practical case, some leakage current will be flowing. Now my question is whether the current in this branch, that is a series branch, will be same or different. Yes, that will be same or different. Come on, same current, yes or no? Series connection, suppose two resistors you are having, the two resistors are connected in series. So what about the current flowing through them? Definitely same, right? So suppose now current flowing through this series branch, let us consider some small current, because they are in a blocking mode now. So that's why let us consider some small current is flowing. Let me indicate that small current is here, right? Suppose this is a small current we have considered. Now this indicates this point is on the current axis and this current is small, so it indicates the current which is flowing in this circuit. So now from this, if I take the projection, it will cut here, and for the second SCR it will cut somewhat here. Okay, here it is, and for the first SCR, suppose it is here it is. Okay, so this is corresponding to that your blue line, and this is corresponding to your green line. Okay, so now you can check here. Let me write it as a VBO1. This is a let me write it as, instead of VBO, let me write it as a VT1 and VT2. that will be better. VT1 and VT2. So this is a VT1 and this is a VT2. Second means blue line. Okay, green means your first SCR. Okay, so for the second SCR you can check corresponding to, yes, intersection point is here. So therefore this is a VT2, voltage across thyristor 2. This is a voltage across thyristor 1. So point to be noted here, even though both the SCRs are having the same breakover voltage, same voltage rating, but they are not sharing equal voltages, right? They are not sharing the equal voltages. So it is like a thyristor T1 is sharing the VT1. So let me write it as a VT1, and thyristor T2 is sharing the VT2, right? So now why this is happening? Why this is happening? Because both the SCRs are not having the exact same, okay, exact same static VI characteristics. Now from this, can we say that you can check here, the leakage current of the first SCR, leakage current of the first means green, huh? Leakage current means what? You can recall the static VI characteristic. Leakage current means what? This indicates the leakage current, na? For leakage current for second SCR is this one. Okay, you can check. Leakage current of second SCR is more, leakage current of first SCR is less. So here can we say that the SCR which is having a lesser leakage current will block more voltage? Is this clear? Right? So please try to understand. Okay, so here let me write. Yes, SCR which has more leakage current will block, yes, SCR which has more leakage current will block less voltage, and the SCR which has a less leakage current, green one is having, first SCR is having a less leakage current, na, right? So and SCR which has less leakage current will block more voltage, Is this clear? Means the thing is, two SCRs are having the same voltage rating, but both are not blocking the equal voltages. Both are not sharing the equal voltages. Are you getting the point, right? So SCR which is having a less leakage current will block the more voltage. You can check now. Less leakage current means what? Less leakage current means more leakage impedance, na? Less leakage current means more leakage impedance. Okay. Now suppose we are having the two impedances connected in series. Suppose instead of two SCRs, we are having the two impedances. Instead of two SCRs, we are having the two impedances connected in series. Okay. Now you can check. SCR1's leakage current is less means SCR1's leakage impedance is more. So this SCR is having a more impedance, leakage impedance. This SCR will be having a less leakage impedance. Okay. So when the two impedances are connected in series, then the voltage across the impedance which is having a more value, okay, across that impedance will be getting the more voltage or less voltage? More voltage will be getting. Na? Suppose we are having the two resistors. Let us consider one is a 5 ohm, second one is a 10 ohm. And across that 5 ohm and 10 ohm series connection, I have connected, let us consider a 15 volt voltage source, right? The question, yes, the circuit is like this. For example, suppose this is a 5 ohm, this is a 10 ohm, and across this I have connected a 15 volt voltage source, plus minus 15 volt. Definitely both are connected in series means current will be flowing same. Yes or no? So what? How much is the voltage across this 5 ohm, and what about the voltage across this 10 ohm? Here it is a 5 volt, here it is a 10 volt. Means the impedance or this resistor whose value is more, across that resistor more voltage will appear. Na? The same is happening here in the SCR's case. The SCR which is having a lesser leakage current means more impedance. Okay. So SCR which is having a lesser leakage current means more impedance, and that will block more voltage. Na? So thyristor T1 here, SCR1 here is blocking more voltage. Is this clear? But now SCRs are blocking or SCRs are sharing voltages unequally. Okay, you can say the unequal. But whether in ideal case, is it acceptable? No, it is not acceptable at all. Right? Is this clear? because the thing is one SCR will be like it is in a more stress, over stressed, and second SCR, right? Second SCR it will be like it is a under stressed. Okay, so that's why what will happen if the case is like, suppose this SCR is having a 250 volt voltage rating, this SCR is also having a 250 volt voltage rating, but suppose first SCR is blocking more voltage and second SCR is blocking less voltage, so there is a possibility of the first SCR getting damaged. So for that we need to avoid this. We need to avoid this. Okay. So for that we are having a circuit called static equalizing circuit. Static equalizing circuit. In static equalizing circuit, what we are doing? We are connecting a resistor R. Okay. Across each thyristor, we are connecting a resistor R, same value of resistor R across each thyristor. So let us discuss how it works. Right. So static equalizing circuit. So suppose we are having the n number of SCRs connected in series. Okay. So suppose we are having n number of SCRs connected in series. This is the first. Let me show it as a second. And similarly, suppose this is a nth SCR. Right. We are having the nth SCR. Right. Next. So this is your first SCR, second SCR, and similarly here it is a nth SCR we are having. Across each SCR we have connected a resistor. Across each SCR we have connected a resistor. Okay, so this full voltage is your string voltage. From here to here, whatever the voltage we are having, it is a string voltage, V string. V string. Right, V string. Let us consider this is R, R, and R. Right, across each SCR we are connecting the same resistor value, that is a R. Right. Next, consider the current flowing through, because all the SCRs are in a blocking mode now. But the thing is, it is like a leakage currents of the SCRs are not same, right? Leakage currents of the SCRs are not same. So here consider the worst case, like one SCR is having the leakage, second SCR number 2 to the SCR number n are having the same leakage current, and SCR 1 is having a less leakage current. Okay, let us consider the case, okay, or the different leakage current. So what happens? So let us consider current flowing through this SCR is a IBMN, right? Next, current flowing through this SCR is IBMX. Similarly, in this SCR, the current is flowing is IBMX. I have given only names IBMN and MX. Means what? This SCR is carrying the minimum current, and remaining all SCRs are carrying the maximum current. Definitely, these currents are leakage currents only. These currents are leakage currents only, right? Consider here current is I1. Here current is I1. Here current is I2. Definitely, if here current is I2 and if this is IBMX, na, definitely here current will be I2 only, na, because here it is IBMX. This is a I2 will be there, right? And suppose total current is a I. This current is a I. Similarly, here current is also I. Now, can we say that I is equal to IBMN plus I1? And again, I is equal to IBMX plus I2. Okay, same thing, right? You can miss indirectly. I'm using here KCL. I'm using KCL at this point as well as KCL at this point. Okay, next, suppose voltage across this SCR. Now, what we discussed, the SCR which is having a less leakage current is blocking more voltage, na? So here thyristor 1, SCR1 is having the less leakage current. IBMN means minimum, okay, minimum leakage current, and IBMX means it is like a maximum leakage current. Okay, so therefore here voltage will be VBMX. Please be careful. Current is minimum, voltage is maximum, right? Same thing we discuss now. Next, similarly here what will happen? This will be like your VBMN. Current is maximum, voltage will be minimum, right? Similarly, we'll be getting here. This is also equal to VBMN. Okay, VBMN. So let me write here. We're having n SCRs n SCRs, okay, connected in series, and we have considered the worst case. Ideal case means what? All the SCRs should carry the same leakage current, right? That is the ideal case. Okay, but in the worst case, what I am considering, 1 minus n SCRs are carrying the same leakage current, and only one SCR is carrying the different leakage current. Okay, so now n minus 1 SCRs, yes, having same leakage current. Same leakage current means the string current. Okay, if we show it on the static VI characteristic, okay, then it will be same for all the n minus 1 SCRs. One SCR is having or carrying, you can say, different leakage current. Right? So like this we are having. Now from this we can write I1 is equal to what? I minus IBMN. Can I write I1 is equal to I minus IBMN? Also, can we write I2 is equal to I minus IBMX? Yes or no? Right? Because IBMN plus I1 means I. So therefore, I1 is equal to I minus IBMN. And again, I is equal to IBMX plus I2 now. So I2 is equal to I minus IBMX. So let me write it as I1 is equal to I minus IBMN. And I2 is equal to I minus IBMX, right? I minus IBMN, I minus IBMX. Next. Now can we write the voltage across the string? String voltage is equal to, you can check here, string voltage means this full voltage is your string voltage, na? This full voltage. Now can we write this voltage is equal to I1 into R plus n minus 1 times I2 into R. You can check I1 into R means this potential difference, na? This potential difference is like voltage across thyristor T1. I2 into R means what? I2 into R means voltage across thyristor T2. Similarly, what is the voltage across thyristor T3? It is again I2 into R, because second thyristor till nth thyristor, we have considered the same current, na? Right? Same leakage current. So therefore here it is a I2 into R into how many times? That will be your n minus 1 times. Okay, so let me write it as V string is equal to I1 into R plus n minus 1 into I2 into R, right? N minus 1 into I2 into R, right? Now, next, further, can we replace this I2 with this expression? Can we replace this I2 with this expression, right? So therefore, let me write V string is equal to I1 into R, or you can write RI1 plus n minus 1 into R into I2. I2 is nothing but I minus IBMX. I minus IBMX. Is this clear? Right? I minus IBMX. So further, can I replace this I? Can I replace this I with I1 plus IBMN? I1 plus IBMN. Yes or no? Right? I1 plus IBMN. So I can write therefore V string is equal to R into I1 plus n minus 1 into R into, I'm writing it as I is nothing but, yes, I1 plus IBMN. I1 plus IBMN. Okay, minus this IBMX as it is. So further we can write which is equal to R into I1 plus n into R. Yes, let me write it as first n minus 1 into R into I1, yes, minus IBMX minus IBMN. You can check the same term. I have taken this minus outside and I have written it as IBMX minus IBMN. Okay, so further we can write it as therefore V string is equal to R into I1 plus n into or n minus 1 into r into I1, okay, minus this n minus 1 into r, okay. Let me write it as n minus 1 into r into this term, IBMX minus IBMN. At the end of this discussion, we'll be getting the expression for the R, okay, expression for the capital R, right? So, which is equal to R into I1 plus N into R into I1, N into R into I1, okay, minus R into I1 minus N minus 1 into R. Let me replace this term, okay, with a delta IB, right? Delta IB. Delta IB means what? Difference in leakage currents, okay, of the SCRs, right? Where delta IB is equal to IBMX minus IBMN. IBMX minus IBMN. This is your delta IB, right? We have replaced now. Now you can check here minus RI1 plus RI1. It will get cancelled out, right? It will get cancel out, right? Next, further, can we write it as, yes, R into I1. You can check here. R into I1 means this is R, here it is I1, is nothing but what? VBMX na. So can I replace that R into I1 with VBMX? Yes. So we can replace it with VBMX. So therefore, V string is equal to N into this R into I1. I am replacing with the VBMX. Okay, so N into VBMX minus N minus 1 into delta IB. Okay, V string is equal to N into VBMX minus N minus 1 into delta IB. Okay, into R is there, right? So into R into delta IB. So from this R, so therefore from this we can write R is equal to, yes, it will be like N into VBMX minus V string divided by this N minus 1 into delta IB. This is the important expression, and this expression is of static equalizing resistance. Static equalizing resistance means if I connect this value of resistor, across each thyristor, then yes, definitely the same voltage will not appear, but nearly same the voltage sharing will be there. Okay, nearly same the voltage sharing will be there. Is this clear? So this is the static equalizing resistance. Please check how we have derived it. Now in this expression, if you check, N means what? Total number of SCRs connected in series. VBMX means what? VBMX is nothing but a maximum voltage shared by that SCR, particular SCR, right? We are having the N SCRs. Out of that, only one SCR we considered that SCR is sharing the maximum voltage. Remaining all other SCRs are sharing the voltage of VBMN, that is the lesser voltage, right? Next, V string means what? Total string voltage divided by N minus 1, yes, number of SCRs minus 1 into delta IB. Delta IB means what? It is a IBMX minus IBMN, means difference in, yes, leakage currents, okay, flowing through the SCRs. Difference in leakage currents flowing through the SCRs. Suppose we are having the two SCRs, na previous case we considered. Then here N is equal to 2. So it is equal to VBMX. Now VBMX means what will be there? VBMX is nothing but, you can check na, in the previous case, V voltage across thyristor 1 was a more voltage na. So here it will be VT1 will appear. Minus string voltage divided by N minus 1 means 2 minus 1 into this delta IB, right? Delta IB means difference between the leakage currents, right? We have shown na leakage currents are different. So that's why the problem is occurring. Okay, so this is the one way or the one method in order to for getting the uniform voltage sharing, right? So yes, next, yes, all your doubts will be answered at the end of the session, right? Okay, so this is the problem associated with the series connection of SCR and how to overcome that problem. Now, let us discuss the problem associated with the parallel connection of SCR. So before that, yes, let me ask a question. Suppose we are having two SCRs. Both the SCRs are having a identical or exact same static VI characteristic. Exact same means what? The static VI characteristic of the first SCR and the static VI characteristic of the second SCR. Yes, these two will be same. Means what? Yes, it is like a ek ke upar second aayega, right? Ek ke upar second aayega. So what will be the string efficiency in this case? Can anyone? Suppose if both the SCRs are having the identical VI characteristic, or you can say the exact same VI characteristic, then what about the voltage shared by leakage currents will be same, na? Means both the SCRs are having the exact same VI characteristics, means you can check from this point. If I take the projection, then the leakage current will be same for both the SCRs. If the leakage currents are same, then they will be having the same leakage impedance. Same leakage impedance means in this case it is like here it is also 5 ohm, here it is also 5 ohm. So what about the total voltage sharing? That will be equal, na? We are having R and R ohm resistor connected in series, okay, and the voltage is V. Then what is the voltage across each resistor? It is a V by 2 and V by 2, right? The same thing will happen. But the problem is in practical case. Yes, we are having the different VI, static VI characteristics. Even though their voltage rating is same, but they are having a different static VI characteristic. That's why this problem is occurring. Okay. So one SCR is sharing more voltage, second SCR is sharing less voltage, right? So that's why the problem is occurring, right? So how to overcome this problem? Yes. How to overcome this problem? The problem we can overcome it by connecting a same value of resistor across each thyristor, and the value of resistor we have derived here expression, static equalizing circuit, right? Static equalizing. Definitely this connection of this resistor will not give you the 100% string efficiency, but it will make the uniform voltage sharing, right? Ideally what we expect, the SCR which is having a high voltage rating should block more voltage, na? This is what the ideal expectation. Okay, ideal expectation is the SCR which is having a higher voltage blocking capacity should block more voltage. This is the ideal expectation actually. Okay, but in real life it is not happening. So that's why we need to connect the number of SCRs in while connecting the number of SCRs in series across each SCR, we need to connect a resistor. Okay, across each SCR we need to connect a resistor. Is this clear? Next. I don't know is this anonymous attendee. Okay. Every time you are asking for a break only, huh? I'm seeing from day one, right? Okay. Okay. Yes. Okay, so we'll take a break here. After the break, we'll discuss the parallel connection of SCRs, right? So almost we are at the end of the SCR. Okay, we're almost at the end of the SCR. After this series and parallel connection, we'll be discussing some numericals, and after that the pulse transformer concept. Why the pulse transformer is required? What is the difference between that pulse transformer and your utility system transformer? That we will discuss. Okay, and one example is there in your booklet related to the pulse transformer, that we'll discuss. Okay, so probably today we'll finish the SCR and we'll discuss the power BJT and if possible the power MOSFET also, right? So tomorrow we'll finish the chapter number 1. Chapter number 1 is a very vast chapter. Okay, n number of concepts we are having here, right? And we are having a detailed analysis of the SCR. So please go through whatever we have discussed, okay, regarding the SCR or regarding your other devices, just like a BJT, MOSFET, GTO, IGBT, right, TRIAC, etc. Okay, so all are important, but most weightage is given to the SCR, right? Given to the SCR. So we'll start at after 20 minutes. We'll start, right? Okay. Okay. All right. So in order to make the voltage sharing uniform in the static in the series connection of SCRs, right? What we are doing, we are connecting a resistor across each SCR. So how the connection of that resistor will help in improving the voltage sharing or making voltage sharing uniform? You can simply check a network example. Suppose we are having two resistors, right? Both are having the different resistance value and they are sharing the unequal voltages. You can connect any value of same value of resistor across them. You can get somewhat improved voltage sharing. Na? The same thing is happening here, right? Definitely, we will not get the efficiency 100%, but we can claim here that we are improving the voltage sharing. Means the SCR which is having a more voltage blocking capacity will share the more voltage, right? And the SCR which is having a less voltage blocking capacity will share the less voltage, right? Next, now before moving towards the parallel connection of the SCRs, let us discuss one more problem related to the series connection of SCRs. And for that, we are having the dynamic equalizing circuit actually. Okay. So the first problem we discussed that when the SCRs are connected in series, due to the difference in their static VI characteristics, okay, the SCRs are having the different leakage currents, and due to that, they are having the different voltage sharing. Now, suppose we are having a n number of SCRs. Okay, suppose we are having or let us consider the two number of SCRs first. Okay, suppose we are having two SCRs connected in series. Suppose we are having two SCRs connected in series. Both are having the same voltage rating. Okay, both are having the same voltage rating. Let me write it as a 1 and 2. Right? Next, suppose for a particular application, we have turned on the SCRs, right? Means both the SCRs are in a on state. Both the SCRs are in a on state. Means you can check with the previous example also. For 0 to 5 seconds, we kept the SCRs in a on state, na? And at 5 seconds, we are turning off the SCRs. But if the SCRs are not having the dynamic characteristics similar, not having the exact same dynamic characteristics, then will be our SCRs will be getting the problem. Okay, right? So which problem they will be getting, let us discuss. For example, suppose we're having the two SCRs, 1 and 2. We already considered these two are connected in series. Suppose the dynamic characteristics of the SCR I am drawing here. Let us consider the current flowing through the SCRs are IA. Yes. Initially SCRs were carrying the current, okay, because they were in the on state, and suppose we're having the characteristic like this. This is for the first SCR, let us consider, and similarly consider for the second SCR, right? So it indicates this is your TRR plus TGR, na? That is a TQ. Let me write it as a TQ1, right? And similarly, let us consider the TQ2. Whether we have discussed this type of characteristic? Yes. Yes or no? Dynamic characteristics of the SCR. Now, suppose I'm saying that these two SCRs are in a on state, right? So suppose SCRs are in on state. Means both are in a short circuit mode, both are in a forward conduction mode, okay? And they are carrying a current. They are carrying a current. No problem. They are working fine. They are working fine. Now, suppose for a particular application, if I want to turn off the SCRs, right? So when the SCRs are turned off, means suppose both the SCRs are having the current flowing through both the SCRs become zero at this instant. Okay, because initially as these two are connected in series, so definitely there will be the same current that was flowing through the SCRs. Let us consider that current is IA, right? In order to turn off the SCR, yes, we have started decreasing the current. Okay, at this instant the current flowing through both the SCRs becomes zero. So definitely our SCRs will turn off. Definitely our SCRs will turn off. But if both the SCRs are having different dynamic characteristics during turn off, if both the SCRs are not having same dynamic characteristics, means different dynamic characteristics during the turn off. These are the dynamic characteristics during turn off, na? So you can check here for SCR1. For SCR1, we're having a dynamic characteristic is like this. Okay, shown with the brown one. Second, we're having with the green one, we're having the dynamic characteristics for the SCR2. Okay, during the turn off. So what it indicates? It indicates that yes, the reverse recovery charge of SCR1 is less than that of reverse recovery charge of the SCR2. Is this clear? Right? So what I am saying, SCRs were in a on state for a particular application. Yes, it is required. Let me write it in short. Okay, it is required to turn off SCRs. Now here what is happening? As both the SCRs are having different VI characteristic, instead of VI, let me write it as a dynamic characteristic during turn off. Okay, so now what, due to that, what is happening? It is like, let us consider the case like a reverse recovery charge of SCR1 is less, right? Is less than that of reverse recovery charge of SCR2. Yes or no? Reverse recovery charge means area under this triangle. Okay, generally we approximate this as a triangle. Okay, and we find the reverse recovery charge, right? So reverse recovery charge of this is less compared to that of reverse recovery charge of the second SCR. So now you can check here, as the reverse recovery charge of the first SCR is less than that of the reverse recovery charge of the second SCR. So what will happen? The circuit turn off time for SCR1 required is definitely less than that of the circuit turn off time for the SCR2. Okay, so that's why what is happening here, our SCR1 will successfully turn off before that of the SCR2. I am saying SCR1 will successfully turn off before the SCR2. So now you can check here. In this case, we are having the two SCRs connected in series, and if SCR1 will successfully turn off before SCR2, so what will happen? The string voltage is a high voltage, na? Suppose SCR1 is turned off successfully and SCR2 is not yet turned off. So what will happen? Whatever the string voltage is there, that full string voltage will appear across the SCR1 only, and that may damage your SCR and your full string will collapse, right? Your string will collapse. Is this clear? So that's why we need to connect a capacitor, okay, across each SCR. We need to connect a capacitor across each SCR. Now, why the capacitor is required here, right? Why we are connecting the capacitor? Because you can check both the SCRs are not turning off at the same instant. Turning off means I am saying that successfully commuted. I am saying, okay, both the SCRs are not successfully turning off at the same instant because they are having the different QRR, that is the different reverse recovery charge. And what is the difference in the reverse recovery charge? If you check this circuit, if you check this waveform, this indicates yes, the difference in reverse recovery charge, na? This indicates the difference in reverse recovery charge. So can I indicate this as a delta QRR? Can I indicate this as a delta QRR? Delta QRR is nothing but difference in reverse recovery charge of the both the thyristors, right? Thyristor 2 and the thyristor 1. Okay, so now means indirectly we need to put a element that can absorb the charge fastly, that can absorb the charge, I am saying. Okay, so suppose if we connect a capacitor across each thyristor, we are having the capacitor that absorbs the charge. Now capacitor stores the charge means what? Capacitor absorbs the charge. Okay, so if we connect a capacitor across each thyristor, definitely it will, okay, it will improve or it will make the turning off of the second thyristor faster, second thyristor faster. Is this clear? So this is the problem associated with the dynamic characteristics of the SCR. Okay, you will not find this point in any of the book, right? So please try to understand here only. Okay, try to write your short notes. Okay, so I am saying that this problem is due to the difference in the reverse recovery charge, okay, of both the SCRs, right? Both the SCRs. So now, so for that, generally a capacitor is connected in parallel or across each SCR. Okay, so suppose we are having two SCRs connected in series. And across each SCR, I am connecting a capacitor. Across each SCR, I am connecting a capacitor. Same value of capacitor. Capacitor opposes the sudden change in the voltage also, right? So suppose this is T1, this is T2. Means when, if suppose T1 turns off early, then what will happen? Yes, whatever the voltage was appearing here na, across T1, that will not increase suddenly because of this capacitor. This capacitor will oppose the sudden change in the voltage na. So in this way, we can protect our thyristor T1. Okay, is this clear? Right? So this is C is nothing but, and this C is given by C is equal to N minus 1 into delta QRR. They have asked the numerical delta QRR divided by N into VBM minus V string. N into VBM means VBMX actually, right? Minus V string. This is the expression for the dynamic capacitance. Dynamic capacitance. Right? We need to connect across each SCR, right? So this is for, this is the dynamic equalizing circuit, and first one we discussed, it was the static equalizing circuit. Now with the dynamic equalizing circuit, we are having one problem. What is that problem? Only connection of capacitor. If you check across SCR, what will happen? When SCR is in a off state, na, this capacitor will be charged to the high voltage, and when SCR is in a on state, it is like our capacitor will go on discharging. Capacitor go on discharging. So it will again cause the same problem as that of your snubber circuit, na, snubber capacitor, right? When the capacitor is connected across the SCR, when SCR is in an off state, our capacitor go on charging, and when SCR turns on, capacitor again discharges, right? So for that, one more resistor is required to be connected, okay, in series with a SCR, sorry, in series with a capacitor. So I'm yes, rewriting this as right. So generally this R and C, and this R and C is connected. Okay, but again, this is like a your snubber circuit, na, right? So same whatever the snubber we are going to connect across the SCR, that snubber can protect. Okay, that snubber can play the role of dynamic equalizing circuit also. Are you getting the point, right? That can play the role of dynamic equalizing circuit also. Is this clear? So let me draw the static equalizing circuit and dynamic equalizing circuit all together, right? So static and dynamic equalizing circuits. So this is your actually dynamic equalizing circuit. So static and dynamic. The static circuit is like a connection of resistor, na? This is a R and R. This will be your static equalizing circuit, right? And for the dynamic equalizing circuit, we are having here R and C. In some of the cases, a diode is also connected, just like this, in order to avoid the losses, okay, during the charging of the capacitor. Right? This is RC, RR, R and C. So it is like this. This is your dynamic equalizing circuit. And here it is a static equalizing circuit. Right? Static equalizing circuit, right? Next. Now let us discuss about the parallel connection of SCRs, right? Parallel connection of SCRs. So why it is required to connect the SCRs in parallel? Yes, can anyone? Why it is required to connect the SCRs in parallel? Yes, more current handling, right? Means if your system working current is greater than, or you can say the load current is greater than the current rating of a single SCR, then we need to connect the number of SCRs in parallel. Okay, so how will be the parallel connection? It will be like this. I'm showing with two SCRs. Suppose here we are having a load. So this is your thyristor T1, thyristor T2, right? This is the supply voltage Vs. It may be AC, it may be DC, anything, right? So suppose if load current rating is, let us consider the 500 ampere, and our single SCR is having a current rating of, let us consider 300 ampere. Then what will happen? Whether our single SCR can resist with that 500 ampere? No, right? So it is like when SCRs are in a on state, when SCRs are in a on state, then and only then the current will flow through the load, na? Right? So here, if the load current, let me write it as a I0, right? If I0, and suppose this is a IT1, that is a current rating of SCR. This is IT1 and IT2. Actually, what is expected? Both should carry the currents proportional to their current rating, but this is not happening in the real case. Why it is not happening, we are going to discuss. Okay, so now first of all, my question is, here we need to consider whether it is a blocking state or the conduction state. In the case of series connection, we focus on which state? Forward blocking state. Now in this case, conduction state only. Why? Because if the conduction state, if the SCRs will be in the conduction mode, then and only then the high current will be flowing, okay, and then only there will be the load current will be shared by among these two parallel branches, right? So now, so let me write here, if load current, you can say load current or system working current, anything you can say, if load current is greater than current rating of single SCR, then we need to connect SCRs in parallel, right? SCRs in parallel. You're getting the point, right? So now again here we're having the two parameters or the two terms. One is the string efficiency and second one is the derating factor. So let me write the string efficiency. String efficiency is equal to, or the percentage string efficiency is equal to string current or you can write string current rating, doesn't matter, divided by number of SCRs connected in parallel into current rating of each SCR right? So, into 100. What is the current rating? String current rating. String current rating is nothing but your I0 only in this case. Okay. So let me write it as either here. I can write it as a I string. You can write, check here. I string is equal to I0 only, na? Right? So here string current rating divided by number of SCRs connected in parallel into current rating of each SCR, right? Current rating of each SCR. So that will give you the string efficiency. Second thing, we are having the derating factor. Again, it is same 1 minus string efficiency. 1 minus the string efficiency. This is the derating factor, right? Next. So now let us discuss the problems associated with the parallel connection of SCR. Okay. Problems associated with parallel connection of SCR. So suppose we're having two SCRs connected in parallel, right? So same circuit I'm drawing. Suppose your load we're having. This is first SCR, this is the second SCR, right? Suppose this is IT1, this is a IT2, and here it is a string current, or you can write I string. And suppose the SCRs are having a static VI characteristic like this. This is a voltage, this is a current, or V and IA you can write. So this is for first SCR. Similarly, let us consider for the second SCR. right? Suppose this is for SCR2. This one is for SCR1. Okay. Next. Now SCRs will be in the conduction mode. Yes or no? Right. So therefore, as these two SCRs are connected in parallel, what about the voltage across them? Whether it will be same or different? We don't know. When branches are connected in parallel, then the voltage will be same, right? So here voltage across first SCR will be equal to voltage across second SCR. SCRs are connected in parallel and they are in a conduction mode, na? So that's why the voltage across SCRs will be like only, yes, it is like an on-state voltage drop, right? So suppose as these two SCRs are connected in parallel, so let me indicate the voltage drop, okay, across the SCRs. Let us consider this one, right? Suppose this is the voltage drop. So from this, if we take the projection here, right, I'm taking the it will be like this. So this characteristic will be like this, huh? It will be extended. So now you can check here. Yes, this is the IA, right? So you can check here this corresponding to this voltage on the conduction, okay, in the on the forward conduction mode, it is cutting here for the second SCR, and for the first SCR it is cutting at this point, right? So can I write this is corresponding to the first SCR current and this is corresponding to the second SCR current. Green one means the second SCR, right? And this brown one is nothing but your first SCR. So even though both the SCRs are having the same current rating, okay, but as these two SCRs are having some different characteristics, that's why they will not share the equal current. They will not share the equal current. Here you can check IT1 is greater than that of the IT2, right? So you can check here on state voltage drop of the first thyristor is very small and the on state voltage drop of the second thyristor is a somewhat more. So can we say that here the SCR which is having a less on state voltage drop will share more current compared to that of the SCR which is having a more on state voltage drop? Are you getting the point? I'm repeating, the SCR which is having a lesser on state voltage drop will share more current compared to that of the SCR which is having a more on state voltage drop. Okay, so let me write SCR which is having less on state voltage drop, less on state, na, for thyristor 1 it is a less on state drop will share more current compared to SCR which has less more on state voltage drop. SCR which has more on state voltage drop, right? More on state drop, right? More the on state drop, lesser will be the current sharing, right? Lesser the on state drop, more will be the current sharing, right? But this is not the ideal case, na? Actually what we expect, right? SCR should, if both the SCRs are having the same current rating, SCR should share the current equally, na? Right? But and one more disadvantage is that you can check here, if SCR1 is sharing more current compared to that of the SCR2, so what will happen here? We know SCR is having a NTC, negative temperature coefficient. If the current flowing through the SCR1 is more, so what about the conduction loss of the SCR1? Conduction loss will be more. More the conduction loss, the meaning is more heat will be generated. More heat generated means what? The temperature of the SCR1 will be increasing. Okay, it will be more compared to that of the second SCR. If the temperature of the SCR1 is increasing, or it will be greater than that of the temperature of the SCR2, so SCRs are having the NTC, the negative temperature coefficient. So if the SCR1's temperature is more, so what about the resistance of the SCR1? Resistance will decrease, na, because negative temperature coefficient means what? Increase in the temperature, decrease resistance decreases. Are you getting the point? So this is very dangerous. If SCR1 is carrying more current, more heat will be generated in the SCR1. Temperature of SCR1 will be increases. Okay, and due to the increased temperature, what will happen? The resistance of the SCR1 will further decrease. If the resistance of this path decreases, then can we say that the current flowing through SCR1 will further increase? Yes or no? So this is a very serious drawback. Are you getting the point? Right? Means what we are expecting? We are expecting that the current flowing through SCR1 should be reduced now, because it is sharing more current. But in actual case, what is happening? Due to the more current, the resistance of the SCR1 is further decreasing. Due to the decreased resistance, the current flowing through the SCR1 is again increasing. Means that current will be again more than that of the, or whatever this IT1. So indirectly, in addition, if it continues like this, it will damage our SCR1, right? So that's why we cannot accept this. So for that, we need to provide a solution. Okay, so what solution we can provide? Let us discuss. Yes, so we're having two possible solutions. One is we can connect a inductor. We can connect a inductor right, like this. Okay, this is like your total string current, I string, and here is SCR1, here it is a SCR2. SCR1 current is like IT1, SCR2 current is like IT2, and this inductor we are having yes. Yeah, now let us discuss what will happen. This inductor, or you can say the coils also. Okay, we have connected the coils in such a way that if currents flowing through these two branches, if currents flowing through IT1 and IT2 are equal, if currents flowing through IT1 and IT2 are equal, that is the same value, then the EMF induced in both the coils will be like a equal and opposite, will be like a equal and opposite. So that's why resultant EMF will be zero. Resultant EMF will be zero. But if there is a difference, between IT1 and IT2, suppose IT1 increased, suppose IT1 is increased, then due to that, what will happen? Due to the increase in the IT1, it is like a voltage induced in this part, that is the V1. Okay, voltage induced in this part, that is the V1. That will be more. That will be more. If this voltage is more, indirectly that will oppose whatever the total voltage here, na, whatever the total voltage across the thyristor T1. Okay, there. So that's why this voltage will oppose, and in addition, the resultant voltage across T1 will decrease, and your current flowing through thyristor T1 will decrease. Means here the EMF, different EMFs are induced if the current flowing through both the thyristors are different. Okay, and the direction of the induced EMF is such that it will, according to the Lenz law, na, it will oppose the cause. It will oppose the cause. So that's why the EMFs induced in the coils will oppose the cause. So who is responsible for the induced EMFs in the coils? The difference in the currents. Okay, so therefore our induced EMF in the coils will oppose the difference in the current, and they are opposing the difference in the current means what? Indirectly they are helping in making the current same, right? In keeping the current same or the equal. This is the one way we can connect, right? Next, the second way is we can place the SCRs, okay, on a heat sink. We can say that it has a symmetrical arrangement. Okay, symmetrical and asymmetrical. Let us discuss first asymmetrical, and then we'll discuss the symmetrical. Asymmetrical arrangement of SCRs. Asymmetrical arrangement of SCRs. And second, we will discuss the symmetrical arrangement. Asymmetrical arrangement means what? Suppose we are having a heat sink. Okay, we are having a heat sink. For example, suppose like this we are having, and we are yes, placing the SCR like this. Suppose this is the SCR1 here, SCR2 here, and here it is a SCR3. For example, suppose we are having the 3 SCRs. Let me write as the first SCR, this is the second SCR, this is the third SCR, right? This is a heat sink, this is a heat sink, HS, that is a heat sink. Now suppose if the current flowing through the first SCR increases, if the current flowing through the first SCR increases, right? Due to that, what will happen? More heat will be generated. Yes or no? Heat generated increases, right? And whatever the heat generated here, this heat will spread like this. Yes or no? Whatever the heat generated here, this heat will spread like this. Okay. So now you can check this heat will first of all come across the second SCR, or second SCR will first of all experience that heat. Due to that, the second SCR's resistance increase. Yes or no? Right? So second SCR's resistance will decrease because NTC na negative temperature coefficient, right? So due to that heat, the resistance, the second SCR's temperature increases, and due to that, the second SCR's resistance decreases. If second SCR's resistance decreases, then more current will be flowing through the second SCR. So indirectly, IT2 will increase. Similarly, whether that heat will stop here? No, the heat will continue, spreads here also. After the second SCR, that heat will be experienced by the third SCR, that will reach to the third SCR. So again, third SCR's resistance decreases due to the negative temperature coefficient, and IT3 will again increase, right? Means IT2 also increase, IT3 also increase. Means whatever the current was there, na string current, initially the IT1 was increased, but now due to the spread of this heat, yes, IT2 also increase, IT3 also increase. Means in addition or resultant, can we say that the current of the thyristor T1 will decrease, because string current means what? IT1 plus IT2 plus IT3. If IT2 and IT3's resistance decreases, so more current will be flowing through the IT2 and IT3. So this can, this can save our thyristor T1, right, from damage. This is the asymmetrical arrangement. But compared to that, we are having one more arrangement, that is a symmetrical arrangement, that is more effective. You can check here. Here, what is happening? The first of all, SCR2 is experiencing the heat, and after that, SCR3 is experiencing the heat. Now, in the symmetrical arrangement, we are going to, yes, put the SCRs like this. Symmetrical arrangement of SCRs. Suppose we are having a heat sink. Okay, this is the heat sink we are having. And we are having the 3 SCRs we have placed. Suppose one is here, second one is here, and third one is here. Suppose this is the first SCR, this is second SCR, this is the third SCR. Now what will happen due to this? Suppose IT1 increases, that is first thyristor's current increases. Okay. Due to that, heat generation increases, This heat will spread, right, like this. Now, can we say that whatever the heat is spreading here, that heat will be experienced by both the, that is the second and third SCRs at the same time? Yes. So at the same time, what will happen? The temperature of your SCR2 and SCR3 will increase. Okay. So SCR2 and SCR3 temperature increases at the same time, I'm saying. Okay. So due to that, what will happen? Both the SCRs are having the NTC, negative temperature coefficient. So due to that, current flowing through thyristor T2 increases, and at the same time, IT3 also increases. So in a asymmetrical, it was like, first of all, second SCR's current will increase, after that third. Okay. But in this case, what will happen? Whatever the additional current was there, okay, that was flowing through the thyristor T1. Okay. So SCR2 and SCR3 will be sharing that current now, right? So this is the one possibility or one way which we are using, okay, in order to protect the SCR from permanent damage due to the increase in a current in a parallel connection of the SCRs, right? So this is symmetrical arrangement of SCRs, right? So next, now let us discuss some numericals. Yeah. Is this visible? Yes, no. Yes. 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 Let us read this question. A thyristor string is made up of a number of SCRs connected in series and parallel. The string has a voltage and current ratings of 11 kV and 4 kiloampere respectively. Means string voltage they have given, string current rating they have given. The voltage and current ratings of available SCRs are 1800 volt and 1000 ampere respectively. For a string efficiency of 90%, first bit, calculate the number of series and parallel connected SCRs. Second bit, for these SCRs, maximum off-state blocking current is 12 milliampere, means IBMX they have given. Determine the value of static equalizing resistance for the string, that is the R value. We have derived the expression for the capital R, right? And third bit, for a thyristors of maximum difference in their reverse recovery charge is 25 microcoulomb. That is a delta QRR they have given. It is a 25 microcoulomb. Compute the value of dynamic equalizing capacitance of this string. Means our value is to find the, our task is to find the capacitor C. That is the dynamic equalizing capacitor. Okay. So one by one, let us discuss. Let us first of all note the data. It is given that string voltage rating of a string, let me write it as a V string, is equal to 11 kilovolt, 11 into 10 to the power 3 volt, right? Next, current rating given, current rating of string is equal to I string is equal to 4 kiloampere, 4 into 10 to the power 3 ampere. The voltage and current ratings of available SCRs. Okay, SCR voltage rating is equal to 1800 volt and current rating is 1000. SCR current rating is equal to 1000 ampere. First bit, let us calculate a string efficiency they have given. Okay, string efficiency is equal to 90%. So it is a 90 divided by 100. So it is a 0.9, right? So first bit, calculate number of series and parallel connected SCRs. So first of all, let us find for series connection, and next we will calculate for the parallel connection. Okay. So for series connection, right? So we know now string efficiency, it is equal to voltage rating of the string. What is the voltage rating of the string? It is a 11 kV divided by number of SCRs connected in series. Let us consider it as a N. N is nothing but number of SCRs connected in series into voltage rating of each string. So into 1800, right? So you can check it is a 0.9 is equal to 11 into 10 to the power 3 divided by N into 1800. So how much will be getting? N is equal to, or let me write as NS. NS. S is for series. Okay. So NS is equal to how much? 6.79, right? But whether we are having a 0.79 SCR, yes, 0.79 SCR, whether we are having, no. So we need to go for one, yes, next integer, that is a 7, right? So number of SCRs connected in series is equal to 7, right? Next, let us check for the parallel connection. Okay, number of SCRs required in parallel. For parallel connection, So for parallel connection, we know string efficiency is equal to current rating of the string. It is a 4 kiloampere, na? So 4 into 10 to the power 3 divided by, it is like a NP into 1000, na? Current rating of each SCR is 1000, right? So NP is the number of SCRs required to be connected in parallel. So therefore 0.9 is equal to 4 into 10 to the power 3 divided by, it is a NP into 1000. So therefore from this we can find NP is equal to 4 divided by 0.9, right? 4.44, right? So it is equal to 5, right? 5 SCRs we require. Next, what about the resistance R? Static equalizing resistance. So second bit, it is given that IBMX, right? Maximum off-state blocking current. Second bit, maximum off-state blocking current, right? Is equal to IBMX. Yes, how much they have given? 12 milliampere, na? Yes, 12 milliampere minus 3 ampere, right? Now, whether they have commented regarding IBMN, that is the minimum off-state blocking current? No, right? So simply we need to consider it as a 0 ampere. Please keep it in mind. Okay. If they have not mentioned anything regarding the minimum off-state blocking current, that is the IBMN, simply consider it as a 0, right? So IBMN is equal to 0 ampere. So now we can write resistance R, static equalizing resistance. R is equal to, we know it is a N into VBMX minus voltage of the string divided by, we are having N minus 1 into delta IB, na? Into delta IB. Now here, therefore, static equalizing resistance R is equal to, here N is nothing but what? We need to write a N series, na? Static equalizing resistance is required in series connection only. Okay. So here N is nothing but your NS. N is nothing but the NS. Okay. So what is the NS we have written? It is a 7, right? So it is a 7 into, what is the VBMX? That is nothing but the voltage rating. Okay. Voltage rating of the each device. You can check, it is a 1800, right? 1800. 1800 minus string voltage is 11K divided by N minus 1, that is a 6 into delta IB. Delta IB is nothing but your IBMX minus IBMN. So it is a 12 into 10 to the power minus 3. So if you check, it is equal to 22 point, right? 22 kilo ohm. 22.22 kilo ohm. Are you getting the point? Means kilo ohm resistance were connecting across each SCR. So that's why your resultant resistance value of that SCR leakage impedance and this resistance in parallel. Okay. So if I connect this value of high value of this much resistance across each SCR, okay, you will be getting the improved voltage sharing or improved voltage sharing, right? Next, second, we are having next one is the capacitance, right? Capacitance C. So we're having the expression for capacitance. We have written C is equal to, third bit, na? Dynamic capacitance. What is the delta QRR they have given? Delta QRR. That is the difference in reverse recovery charge. They have given. It is a 25 microcoulomb. So it is a 25 into 10 to the power minus 6 coulomb. Okay, 25 into 10 to the power minus 6 coulomb. Now next. So C is equal to, yes, we are having n minus 1 into delta QRR divided by n into VBMX minus V string. Na? Now here we need to consider this n as a NS or NP. Come on. This n will be here NS or NP. NS or NP. Some are saying NS, some are saying NP. NS means series connected SCRs, right? NP means parallel connected SCR. So, yes, dynamic capacitance or dynamic equivalent circuit is associated with which circuit? Whether which connection, series connection or parallel connection? It is associated with the series connection only, na? Yes or no? When SCRs are connected in series and supposing first SCR turns off early, then the whatever the voltage across the string is there, that full voltage will appear across that first SCR. SCRs are connected in series, right? Static and dynamic, we are having, right? These two equalizing circuits are associated with your series connection of SCRs only, right? So here we need to write it. N is nothing but NS we need to write. Okay. Now let me write. In our case, N is equal to NS. N is equal to NS. Don't get confused. Here we need to write NS only. So therefore C is equal to NS minus 1 into delta QRR divided by NS into VBMX minus V string. Is this clear? So is equal to, it is like 7 minus 1. So 6 into delta QRR, 25 into 10 to the power minus 6 divided by NS, that is a 7 na? Into VBMX 1800 minus 11K. So if you check, this is equal to yes, it is a 93.75 na? Nano coulomb, sorry, nanofarad. 93.75 nanofarad, right? This is the required value of the capacitor. Is this clear? Okay, okay. How to know delta QRR? Delta QRR, they have directly given, na? You can check question. For this thyristor, maximum difference in their reverse recovery charge, na? 25 microcoulomb. They have directly given, na, delta QRR. Yes or no? Right? Okay. Now, some students are asking that why it is a NS. Why it is a NS? You can check, na? Dynamic capacitor is associated with your series connection only. We have discussed this concept. Here it is dynamic equalizing circuit, right? So you can check in this circuit here. Just a minute, let me reduce some percentage. Okay. So we discussed here, when SCRs are connected in series, na, then only this problem we addressed, right? So we need to connect the series connection of SCRs only. Is this clear? Next. Sir, how would the circuit look like for this question? Actually, here the circuit will look like means we will be having this parallel connection different circuit and series connection different circuit, Are you getting the point? Okay. Because we are having the SCRs which are carrying the different currents and the different voltages. So if you want one generalized circuit, let us discuss this question. We were here, no? Right. Yes. Let us discuss one more numerical so that it will give you an idea regarding the series and parallel connection. Suppose my string voltage is equal to, like, let us consider it as a 5 kilovolt. String voltage is 5 kilovolt. Okay. And voltage rating of each SCR, is equal to, let me write it as a 1 kilovolt. String current rating, let us consider it as a 4 kiloampere. Right? Next, suppose current rating of each SCR. Current rating of each SCR is equal to, suppose it is a, let me write it as a 500 ampere. Then my question is, suppose string efficiency is 100%. Consider string efficiency is 100%. Okay, is 100%. And my question is, how many number of total SCRs required? Okay, how many number of total SCRs required, okay, for this connection, or you can see, yes, for this connection. So please let me, yes, discuss this. This is the data I have given. If you give the string efficiency, if you consider string efficiency 100%, then we can draw the circuit like a series and parallel all together. Okay. But if the string efficiency is different, they have given, then we cannot draw a single circuit of series and parallel. Then it will be like you are having a separate circuit for series and separate circuit for parallel. So now here, suppose we are having a string voltage of 5 kilovolt. Voltage rating of each SCR is 1 kilovolt. String current is 4 kiloampere. Current rating of each SCR is 500 ampere. Consider string efficiency is 100%. Then how many number of SCRs we require? So my question is, if string efficiency is 100%, whether all the SCRs will be having the exact same static VI characteristics or not? Yes or no? If string efficiency is 100%, the static VI characteristic is same, right? All will be having the same, right? So now, if all are having the same static VI characteristic, so suppose SCRs are connected in series. For example, suppose SCRs are connected in series, then what about the leakage current that will be flowing through each SCR? Whether it will be same or different? That will be same or different? Same only, na, right? Because static VI characteristics are identical, na? Static VI characteristics are identical. So that's why they will be having the same when SCRs are connected in series, and when they are in a blocking mode, then the current flowing through all the SCRs will be same only, right? So that's why all the SCRs will block the same voltage, na? Yes or no? If static VI characteristic is same, that is exact same or identical, then we can say that all the SCRs will block the same voltage. Similarly, as the static VI characteristic during the conduction mode also same for all the SCRs, then can we say that all the SCRs can carry the same current? Whether whether in this case we will be having the difference in a current sharing of the SCRs? Yes, no? Whether they will be sharing the same current or different current? They will be sharing the same current, na? Are you getting the point? My question is, suppose, let me draw here static VI characteristic. This is your VA. This is your IA, right? So this will be like this. So this is the static VI characteristic for the first SCR. Same for second SCR, same for third SCR, same for fourth SCR, and so on. Means for all the SCRs, we are having the same static VI characteristic. So now you can check when SCRs are in a off state. Okay, so it is like a yes, same. We can say that the same current is flowing here. So whatever the voltage blocked by them, it is the same only, na? Right? So all the SCRs will share the equal voltage during their off state. Then and only then we can get the string efficiency 100%. Otherwise, we cannot get the string efficiency 100%. Okay. Next, similarly, suppose all the SCRs are in a conduction mode. SCRs are connected in parallel, and all the SCRs are in a conduction mode. So corresponding to the conduction mode, what will happen? They will be having some voltage. And if I take the projection from this, it will cut somewhat here. Okay. So here from this, we can say that all the SCRs are carrying this much of current, and all the SCRs are, yes, blocking this much of voltage. Yes or no? IA dash, and let me write it as VA dash. So voltage blocked by each SCR is the same. That is the voltage shared, we can say, and current shared by each SCR is also same. So that's why our string efficiency is 100% now. Now here, how many number of SCRs are required to be connected in series? Number of SCRs in a series. You can check if the string efficiency is 100%, then how many number of SCRs we require? Total string voltage is 5 kilovolt divided by number of SCRs in series. Okay, let us consider it as a NS into what is the voltage rating? It is a 1. So therefore NS is equal to 5. Are you getting the point? Each SCR is blocking a 1 kilovolt. So total voltage, total number of SCRs we require 5 SCRs. Okay, so 5 into 1K, that is your 5K. So it is equal to 5. Are you getting the point? Similarly, number of SCRs connected in parallel, that is the NP. How many SCRs are required to be connected in parallel for a string efficiency of 100%? Come on. 8, yes or no? Right? 8 SCRs we require because each SCR is carrying a current of 500 ampere. Total current is 4 kilo ampere. So 4 kilo divided by 500 means 8 SCRs we require. Right? So we require 8 SCRs. So 8 SCRs are required to be connected in parallel. Each SCR's current rating is 500 ampere only. Each SCR's voltage rating is 1 kilovolt only. And our string voltage is 5 kilovolt. Our string current rating is 4 kilo ampere. Okay, so let us discuss how the connection will be and how many total number of SCRs we are required to be connected in this circuit. Okay, so let me write here. Yes, first thing is we require 8 number of SCRs in parallel and 5 number of SCRs in series. Okay, so I'm writing it as a 5 number of SCRs in series. This is first SCR, second SCR, third SCR, fourth SCR, and here it is a fifth SCR. All the SCRs are blocking a voltage of 1 kilovolt, so all together will be the 5 kilovolt. Yes or no? But now what about the current flowing through this branch? Yes, come on. What will be the current flowing through this branch? My question is, when SCRs are in a conduction mode, how much current these SCRs can carry? Yes, when SCRs are in a conduction mode, how much current these SCRs, yes, can carry? Only 500 ampere, na? Right? Only 500 ampere. So here current is only 500 ampere. And voltage here is, it is like a 1 kilovolt. This is like a 1 kilovolt. This is like a 1 kilovolt. Similarly, this is also 1 kilovolt. and this is also 1 kilovolt. Now we are having one series connection of 5 SCRs. They are all together blocking 5 kilovolt, but they are carrying a current of only 500 ampere. But our string current is 4 kilo ampere. So how many such branches are required to be connected in parallel? Yes, we require 7 more branches now, right? So you can check here. Same, we need to repeat it here. Here it is 1 SCR, second SCR, third SCR, fourth SCR, and here it is a fifth SCR. Is this clear? You can check these two are connected in parallel. This is 500 ampere. This is a 500 ampere. Now these two are carrying a total current of 1 kilo ampere. Yes or no? So similarly, we require third branch. Yes or no? Next, we require fourth branch. We require a fifth branch. We require a sixth branch, seventh branch, and similarly the eighth branch. Means here we'll be having like these branches: SCR1, SCR2, SCR3, SCR4, and SCR5. Right? So this type of circuit we require. This is carrying a current of 500 ampere. Similarly, this will carry a current of 500 ampere. This branch will carry a current of 500 ampere. I have not shown here, but here, yes, consider 5 SCRs are connected in series like this. Okay, so this is a 500 ampere. This one will be the 500 ampere. Okay, and this one will be the 500 ampere. You can check here. Let me reduce some percentage here. Right, you can check here how many branches we are having. 1, 2, 3, 4, 5, 6, 7, and 8 branches. Okay, now this will form your string. Okay, so what is the string current rating? It is a 4 kilo ampere. This is your A and B. This is a string. And what is the string voltage rating? Means this string voltage rating. This is your 5 kilovolt now. So how many number of SCRs altogether we require? It is like a 8 into 5 means 40 SCRs we require. Are you getting the point? Right? But if the string efficiency is 100%, we can draw this type of circuit. Right? Is this clear? Right? Okay. Yeah. So this is about the series and parallel connection of the SCRs, right? Series and parallel connection of SCRs. Now let us have some discussion on pulse transformer. Pulse transformer. Yes. So first thing is why the pulse transformer is required. Let us discuss. And after that we will discuss what is the pulse transformer actually. If you check in SCRs, we are having the circuit like this is an anode, cathode, and gate of the SCR. This is an anode, cathode, and here it is a gate. At this side, we are having a high voltage supply, and load is there, no? So that's why high current is there, right? Load resistor RL, and this is a high voltage supply, na? Right? In order to drive the load, in order to fulfill the requirement of the load. So here we require a high voltage, and also the load is also having the current rating, which is a high, right? So that's why across anode and cathode, we are having a high voltage, high current circuit. But whereas you can check across gate and cathode, we are having, yes, very low voltage circuit, low voltage and low current circuit. So it is like this, na? ES we are having. So this is a ES, here it is a RES, and this current is a IG, and this voltage is a VG. This voltage is a VG, right? So comparatively, VG, IG values are very less. Your IA, okay, and your VS values are very high. Okay, so I cannot connect directly here the high voltage and the high voltage high current circuit and here low voltage low current circuit as it is directly. We need to provide a isolation between them, right? So for that the pulse transformer is used. Okay, pulse transformer is used. So how the pulse transformer is connected, let us discuss. Generally between these two points, gate and cathode, we use the pulse transformer. So pulse transformer is like this. It is represented like your transformer only. Generally it is a 1:1 transformer, 1:1 transformer only. Okay, so now we know now transformer is a static device which transfers electrical energy from one electrical circuit to the another electrical circuit without the by keeping the same frequency. Okay, so same here at this side we are having the, yes, whatever the source here na, ES and RES, that will be connected at this side, and here at the output side, okay, this will be given to the gate and cathode of the SCR, gate and cathode of the SCR. So I'm writing here to gate and cathode of SCR, and here we are having from these terminals are, okay, these will be connected to from ES and RES, okay. Generally you might be thinking that here we are having a DC voltage, then it will be like how the transformer can work on DC supply. No, generally we put a switch, because we know now we are having the gate current, it is like a pulse na, we are having a gate current, it is a pulse, it is not a constant current na, it is a pulse type we are having, right? So that's why we are generally in numerical you will discuss whatever we are going to discuss in the next numerical, you will understand. Generally we connect a switch there, right? Next, so this is the function of the pulse transformer. Now what is the difference between the pulse transformer and your utility system transformer? Utility system means what? In power system, whatever the transformers we are using now, those are the utility system transformers, right? So let us discuss the difference. Conventional transformer and pulse transformer. Is this visible? Whether this table is visible to all? Yes. Yeah. So here first one is the conventional transformer which is used in the utility system. Second one is a pulse transformer which is used in a SMPS circuit, switched mode power supply. Okay, so the voltage and current nature or the waveform in the utility system transformer or the conventional transformer, if you check, we are having a pure sinusoidal na, sinusoidal voltage, sinusoidal current, right? Because we expect na in power system, what we expect, the transformer secondary should give the sinusoidal voltage only. So for that in electrical machines you might have studied, if I want, okay, the sinusoidal voltage to be induced at the secondary side, okay, which type of the flux we need to we need to be having in the transformer core. Okay, we will be having the flat topped, yes or no, we will be having that peaky wave type of and those things, right? So therefore it is a sinusoidal. Whereas in a pulse transformer, generally this is used in a SMPS circuit. Okay, SMPS means that you will understand in a DC to DC converter chapter. Okay, here the nature is a non-sinusoidal, because just now I told you for the pulse transformer the input is like it is a DC, but it is having a pulse. For some time it will be having a non-zero value. For some time again it will be having a zero value. Means it is like a pulse. It will be like a pulse. This type of non-zero, zero, non-zero, zero, non-zero, zero. So whether it is a sinusoidal or non-sinusoidal, it is a non-sinusoidal only. But it is not your pure DC na. So that's why your transformer will work here. Are you getting the point? Some of you might be thinking that in on a DC the transformer will act as an open circuit, but this is not a DC here. And you can check what is the switching frequency here. Switching frequency is very high we are having. Yes or no? Switching frequency is very high, right? So next, frequency range. Yes, same thing, frequency range. In the conventional transformer we are having a 50 to 60 hertz. In India it is a 50 hertz. In USA if you check it is a 60 hertz generally. But whereas in a pulse transformer, the switching frequency is very high. It is in the range of kilohertz. It is in the range of kilohertz, right? So next, here the frequency is nothing but the switching frequency I am saying in the case of pulse transformer. Okay. Power rating of the conventional transformer is a medium to high, right? Low, medium power and a high power, because they are usually in a power system, na? And they are designed to handle more power actually. But whereas if you check the power rating in a pulse transformer, it is comparatively very less, because you can check the input voltage and current which we are giving to the pulse transformer is a very less, na? So that's why the power rating is very less, right? Very less. Next, unit of the rating in a utility system transformer, the transformer rating is given in volt ampere, na? Kilovolt ampere, MVA, KVA we are having, right? So it is in a volt ampere. But whereas in a pulse transformer, it is in a volt second. It is a volt second. The volt second is nothing but the product of voltage, and second is nothing but the pulse width of your, yes, pulse width of this signal. Okay. Second is nothing but this pulse width actually. This is the TP, na, generally we say. So that TP into the voltage, right? That will be maximum voltage that will be appearing across this primary, right? Product of these two, that is nothing but your volt second. Okay. Volt second. It is given in volt second. Please be careful. The same we will discuss in the numerical next, whatever we are going to discuss. The next, the core material used. Yes, here the point is interesting. In a conventional transformer, we generally use a soft magnetic material. Why? Because in a soft magnetic material, we are interested in a conventional transformer, we are interested in reducing the hysteresis loss and the eddy current loss. Okay, so for that we are preferring the soft magnetic material. We're having the soft magnetic, we're having a hard magnetic material. In the soft also we're having the different things, na? But in that also we are preferring the silicon steel. Yes or no? Generally we use the silicon steel material, right? So here silicon steel material. Next, but whereas in here pulse transformer, we are using the hard magnetic core. Why we are using the hard magnetic core? The reason is the hysteresis loss, you can check hysteresis loss as well as eddy current loss, it takes place in a core part of the transformer, right? So in order to minimize these losses, you can check the expression of hysteresis loss and the expression of the eddy current loss. Hysteresis loss is proportional to your frequency. Eddy current loss is also proportional to your frequency. Yes or no? Hysteresis loss, I think it is a Bmax to the power something 1.6 into frequency, and eddy current loss is proportional to your Bmax square, okay, or V square into F square, something like this. Okay. So here in both the cases, eddy current loss as well as your hysteresis loss, both are proportional to the frequency. And if you check the frequency range, na, if you check the frequency here in a pulse transformer, it is a very high, right? So in order to minimize those losses, okay, I cannot directly go for the soft magnetic material here. I need to go for the hard magnetic material only, right? So purpose of hard magnetic material is to reduce the core losses in a transformer, pulse transformer. Why? Because in a pulse transformer, the frequency range is in kilohertz. So that's why if frequency is kilohertz, so if I use the soft magnetic material, our hysteresis and eddy current losses will be very high. So that's why we prefer the hard magnetic material. Hard magnetic material means just like your permanent magnet, okay, where generally the dipole movement, okay, you might be knowing, I don't know whether you might be knowing the dipole and those things, okay. In that magnetic core, we are having the dipoles, and in order to change the orientation of the dipole, okay, we are actually applying the MMF, magnetomotive force, right? That concept actually there. Okay, anyways, so we are using soft magnetic material and the hard magnetic material here, right? So this is the difference between conventional transformer and the pulse transformer. Okay, they have asked the question in some of the examinations, what is the unit for the rating of the pulse transformer? So keep it in mind, it is a volt second. Which material is preferred in the pulse transformer for the core? Okay, it is a hard magnetic material is preferred. Okay, generally it is a ferrite core. Okay, generally it is a ferrite core, right? Next, now let us have some discussion on this numerical. Yes, this is in the booklet. Yes. A 1:1 pulse transformer is used to trigger the SCR. in the adjacent figure. Okay, so here we are having a pulse transformer. You can check this PT is nothing but pulse transformer, and they have given it as a 1:1. Generally, we are using 1:1 transformer only, because here our task is only to isolate only to isolate the low voltage and low power, or the low current circuit and the high current circuit, right? So that's why 1:1 transformer is used. But whereas in utility system transformer, you are having step up, step down. Here it is not required, right? Next, a 1:1 pulse transformer is used to trigger the SCR in the adjacent figure. The SCR is rated at 1.5 kilovolt, 250 ampere, with the IL is equal to 250 milliampere latching current, and holding current IH is equal to 150 milliampere. Means they have given the SCR current rating, SCR voltage rating, the latching current and the holding current. And IG max, maximum gate current allowable, is 150 milliampere. Okay, right? So maximum gate current allowable means here they have given, right? This is your IG max. This will be your IG. This will be your IG, because this is a gate terminal, this is a cathode terminal, right? Here it is a cathode and this is a gate terminal. So that's why IG will be here. Next, right? And IG max is 150 milliampere. IL is 250 milliampere. IG mean is 100 milliampere. The SCR is connected to an inductive load, right? Here we are having the inductive load, where L is 150 millihenry in series with a small resistance. Small resistance R is given, and the supply voltage is 200 volt DC. Supply voltage is given, it is a 200 volt. This is a supply voltage, 200 volt DC. The forward drops of all transistors, this statement is important. The forward drops of all transistors, diodes and gate cathode junction during on state are 1.0 volt. Means if the transistor is in a on state, then we need to consider the voltage drop across that transistor is 1 volt. If the diode is in a on state, we need to consider the voltage drop across that diode is 1 volt. And the gate to cathode circuit drop is also 1 volt. Okay, next, the resistance R should be, because in gate and cathode we are having a PN junction only now, we have discussed that, right? Next, the resistance R should be, means we need to find the value of this resistance R. What is the value of resistance R? We need to find, right? So they have given the 4 options. Next, second, the minimum approximate volt second rating of the pulse transformer suitable for triggering the SCR should be, they have given in bracket, volt second rating is the maximum of the product of the voltage and the width of the pulse that may be applied. Okay, means it is a product of voltage and the pulse width. Okay, right? The product of these two, because pulse width is in second, voltage is in volt now. So that's why it is a volt second, right? So that we need to find. So let us first discuss the first numerical. Now here you can check, our task is to find the value of resistance R. What is the function of this resistance R? This resistance R is connected to the gate terminal now. What is the function of the resistance R? To limit the gate current, yes or no? To limit the gate current, because if the gate current is greater than the IG max, our gate cathode circuit will get damaged now. So that's why to limit the gate current, this R is connected. So whether this R value should be such that, we need to put the R value such that the gate current flowing through the SCR should not be greater than this IG max, should not be greater than this IG max. Are you getting the point? Okay. Next, why this capacitor is connected? Actually, let me tell you, this circuit, whatever this circuit they have given here, this circuit is like a isolated type DC to DC converter that is there in the syllabus of ESC, right? But for the gate syllabus, it is not there. Isolated type. Okay, so this circuit is now for what purpose this capacitor is connected? This capacitor is connected to maintain the constant voltage across gate and cathode, right? Means VG to be constant, because VG means where here it is plus, here it is minus, where I'm going VG na, right? So to maintain the constant VG, this capacitor is there. Okay, next. Now yes, let me redraw this network and so that we can solve this. Yes. Here we're having a 10 volt. Let me draw here. It is like this. Okay, this is plus minus. This is a 10 volt here we're having. It is a thyristor, right? It is a ground. This is a pulse, right? This pulse they have given. Means we are having a switching here, right? So it is not like that for the transformer we are having a constant voltage. No, right? This we are having the voltage. For some time it is a non-zero, next zero, non-zero, and again zero, right? Like this we are having. So this transformer, this this transistor is operated like this. Okay, on and off like this. Next, so here we are having 1:1 pulse transformer. PT means pulse transformer. It is not your potential transformer. Potential transformer is there in measurement. Okay, so this type of circuit we are having. High value of inductive load. This is like this. This is a L value. This is a 1 ohm. It is a SCR, capacitor, and resistor R. Our task is to find the value of resistor R, right? Now let us discuss how this circuit operates. Yes, when this transistor is in a on state, when this transistor is in a on state, then and only then the current will be flowing into this branch. Then and only then the current will be flowing into this PT. When transistor is in off state, it is like an open circuit. If this is an open circuit, whether the current will flow through this part, current will not flow through this part. Okay. So now you can check when transistor is in a on state, means it is like acting as a on state. If transistor is in a on state, how much voltage drop is there across transistor? It is a 1 volt they have given now. So here we will be having the voltage drop of 1 volt. Here we will be having a voltage drop of 1 volt that will be taking place. Here total voltage is 10 volt. Total voltage is 10 volt. Out of that 1 volt is, yes, it is a drop here. Because you can check this is like a source, positive plate, negative plate, and that negative plate will be connected again to here. Okay. So total potential difference is 10 volt. Out of that 1 volt is drop here. So how much voltage we can get here? This voltage is equal to 9 volt only. Na? When this transistor is in an on state, here we will be getting the voltage is equal to 9 volt only. Is this clear? Right? Now if this is a 9 volt, definitely here we will be getting it as a 9 volt because it is a 1:1 transformer. If this is a plus here, minus here, this diode will be in the conduction mode. So due to that 1 voltage drop, 1 volt voltage drop will be there in this diode. Yes or no? Right? After that, what about this diode? This diode will be in the off state now because reverse bias. So this diode will not conduct. Right? After that, what will happen? Yes, you can check here. After this diode, current will flow through the resistor R. Next, same your capacitor will be getting charged, and here we are having the, yes, cathode is here, and here it is a anode, and here we are having the gate terminal actually, right? Gate terminal. So you can check here, whatever the current is flowing here, the same current, yes, it will be flowing through the gate and cathode circuit. And in the gate cathode also, they have given the drop of 1 volt, gate cathode junction, they have given the drop of 1 volt. So can I say that this voltage, okay, between gate and cathode also we are having a voltage drop of 1 volt. So now can we say that here? If you check, here we are getting a 9 volt, definitely here we will be getting a 9 volt. 9 minus 1, 8 volt will be getting here. 8 minus this 1 volt drop, that is a total we will be getting it as a 7 volt only. Are you getting the point? Right? Means what is the voltage that will be appearing, right? What is the voltage that will be appearing across this resistor is equal to 7 volt only, na? That will be equal to 7 volt. You can check 9 minus 8 means 9 minus 1 means 8 volt here. 8 minus this 1 volt is there, right? So that's why here we'll be getting only across this resistor, the voltage will be equal to 7 volt only. Is this clear? Let me show here. Voltage across resistor. Let me write it as a VR. Plus minus, this is a VR. You can apply KVL to this secondary, KVL to the secondary part of the pulse transformer. KVL to secondary of pulse transformer. It is like a +9 minus voltage drop across diode, that is a 1 volt, minus VR minus voltage across gate and cathode, it is a 1 volt, which is equal to 0. So therefore VR is equal to 7 volt. We'll be getting VR is equal to 7 volt only. So voltage across resistor is 7 volt we are having. Now can we find the value of resistor? Yes. So therefore resistor R is equal to VR upon, what is the function of that resistor? To maintain the gate current, okay, up to your maximum limit. Okay, what is the maximum limit? It is a IG max. IG max, right? So it is equal to, you can check, 7 divided by IG max. What is the IG max we are having? It is a 150 milliampere. 150 into 10 to the power minus 3. So you can check, it is equal to 7 upon 150 into 10 to the power 3. No? It is a 46.66 ohm. So roughly it is a 47 ohm. Okay, roughly it is a 47 ohm. Next, if this transistor is in an off state, then what will happen? For this circuit, if you check, because they have, if you recall that, if you check that isolated type DC to DC converter, actually one inductor is required here, but they have not given. So if the inductor is not there, then it is like, when this is in an off state, na, then circuit will be at like your rest position. So it doesn't matter, means your gate pulse will be like of 0. Gate pulse will be of a 0 value, right? Next, gate current will be 0, we can see. So R required is 46.66 ohm. This is the one thing. So if you check the options, yes, they have given the 47. Second bit, the minimum approximate volt second rating, minimum approximate volt second rating of the pulse transformer suitable for triggering the SCR should be. Volt second rating is the maximum product of the voltage. Maximum of they have maximum they have said, okay, maximum of product of the voltage and the width of the pulse that may be applied. Okay, width of the pulse we need to find. Means we need to find the width of the pulse, means like this. Then and only then we can find the second bit answer. So we are having the gate current, it is like this. It is a pulse here. So this is TP. This is T. T plus TP. And this is a T, right? This type of pulse we are having, and we are having the pulse width is nothing but this one. This is a pulse width. How generally we calculate this pulse width? How generally we calculate this pulse width? Whether we have discussed the numericals? Yes or no? Whether we have discussed the numericals for calculation of the pulse width TP, knowing the latching current? Yes or no? Right? We have already discussed. That's why they have given here latching current, right? That's why they have given the latching current. Are you getting the point? Okay. So here the latching current is 250 milliampere. So for this, now we need to simplify this circuit. We need to simplify this circuit. So it is like for t greater than 0, we can consider SR is in an on state. Okay. And we can draw this circuit. Anode cathode circuit, I am saying anode cathode circuit. Okay. So let me write for t greater than 0. We can draw the circuit. It is like this. We are having a resistor 1 ohm. It is an inductor here, and it is a source. SCR, it is acting as an on state. SCR is acting as an on state. So this is a 1 ohm. Inductor value they have given. Yes, it is a 150 millihenry, na? 150 millihenry, and supply voltage 200. So it is a 150 millihenry and supply voltage 200 volt. And this current in the circuit is I. So till which instant we need to maintain the gate pulse? Till I reaches the IL, na? I reaches the IL. So now we need to write the expression for this current I. You can apply KVL. You can take the Laplace transform and you can find it. I am writing directly I is equal to, because we already discussed this type of numericals. Okay. So I is equal to, it will be like a 200 divided by the steady state final current. So it is a 1 into, it will be like 1 minus e to the power minus t by tau. So minus t upon tau, that is nothing but 150 into 10 to the power tau is nothing but L by R, right? So it is a divided by should be there. This is a 150 into 10 to the power minus 3, right? This type will be getting current I expression. Okay. Next, what we can do at T is equal to TP, I is equal to IL. At T is equal to TP, I is equal to what? It is a IL. So therefore we can write, therefore, let me write here, IL is equal to 200 into 1 minus e to the power minus TP, right? Divided by this is 150 into 10 to the power minus 3. What is the IL? IL they have given. Yes, if you check IL, it is a 250 milliampere. 250 into 10 to the power minus 3 is equal to same 200 into 1 minus e to the power minus TP divided by 150 into 10 to the power minus 3, right? So from this we can find TP. Okay, we need to find the TP. So it is like 250 into 10 to the power minus 3 divided by 200. So it is a 1.25 into 10 to the power minus 3 is equal to this term, right? So 1 minus e to the power minus TP divided by 150 into 10 to the power minus 3. So therefore we can write it as e to the power minus TP divided by 150 into 10 to the power minus 3. Okay, is equal to 1 minus this term. Na? So it is 1 minus this term. So it is a 0.99, 0.99875. So that's why now we can take the natural log on both sides. Taking natural log on both sides. So we can write it as a minus TP upon 150 into 10 to the power minus 3 is equal to natural log of this term 0.99875. So if you check, it is equal to minus 1.25078 into 10 to the power minus 3. So this minus will get cancelled out, right? So therefore from this we can write TP. This term will be shifting this, right? So it will be like into 150 into 10 to the power minus 3. So it is 1.876 into 10 to the power minus 4. 1.876 into 10 to the power minus 4 seconds. Na? This is required TP. This is a required TP, right? Now if this is a TP, can we find the volt second rating? So therefore volt second rating, right? So therefore volt second rating is, be careful. Huh? They have given the volt second rating means what? Maximum of product of. So volt second rating is the maximum product of the voltage and the width of the pulse that may be applied. So what is the maximum voltage that will be applied? It is a 10 volt. And what is the pulse width? We need to consider this as a, this is TP. So it is a 10 into, because we are calculating the rating here, not the exact value, 1.876 into 10 to the power minus 4. So if you check, it is equal to, yes. Yeah, we can write it as a 1.876. Yeah, 18.76 into 10 to the power minus 4. Or let me write it as 1876 microsecond. But if you check the options, in the options, you will not get this answer. Why? Because 1876 not microsecond, this is a micro volt second, right? That will be micro volt second because it is a volt second rating, na? So that will be your micro volt second. Now, yes, in the options, if you check, yes, you will not get this rating. Why? Because this is the actual rating we have calculated. But while designing the transformer, this is very odd number, na? 1876 microvolt second. Whether we are designing, designing this odd numbered volt second rating transformer, no. So that's why while selecting, we need to go for nearest higher integer, right? So it is like a 2000 microvolt second. We need to select, right? Nearest, but it is a greater than this value, right? Greater than this value. Okay, so it is a 2000 volt microvolt second. So if you check the options, it will be 2000 microvolt second, right? Microvolts. Is this clear? Please go through this numerical, right? Sometimes they have asked the questions based on the pulse transformer also, right? So again, this is not the unique diagram. Let me tell you, this is not the unique diagram, okay, of using the pulse transformer like this. Okay, they may change the circuit, okay, and they may ask the question also, right? So okay, so we'll stop here. No. Maximum applied voltage they have asked the Nagasai. It is definitely across pulse transformer we are getting 9 volt, no problem. But they have asked the maximum applied voltage, right? Yes, repeat second bit. The same second bit I am repeating. Okay. So second bit means what? It is like calculation of TP only. We have discussed this type of questions previously also, na? Means we need to maintain the gate pulse till SCR current reaches the latching current. So here we have considered T is equal to 0. The gate pulse is applied to, this is a SCR. Gate pulse is applied to the SCR and our SCR turns on. Once SCR turns on, current will be flowing into this loop, na? So when the current flows into this loop, yes, we have written the expression for this current. I have written it directly because already for RL circuit, we have derived these type of expressions. Okay. So that's why I have written it directly. Next, at T is equal to TP, I required is equal to IL, na? Right? So that's why further simplifications, sorry. So that's why the further simplifications we are having, and accordingly we have calculated TP. Once TP is calculated, volt second rating, they have given maximum of applied voltage. So maximum voltage is 10 volt applied voltage. Please be careful. Don't consider here the voltage across pulse transformer. Okay. So it is a 10 volt into 1.876 whatever TP we got. Right. So like this, we have got this answer. Right. So stop here. If you are having doubts, please ask.
Hello, good evening, sir.
Yes, good evening.
Sir, is there any shortcut method for if R and C are in series for direct correct current equation?
RL, RC, you are saying?
RL, R and C. Resistor and capacitor.
RL and RC.
Yes, sir. Yes, sir.
Just a minute. Let me allow.
Like in the first problem, you have to the Laplace transform and solve that.
Yes. For RC, I will tell you how to simplify it. Just a minute. Okay. Simply, you can write. Suppose this is the VS we are having. Okay.
Yes, sir.
And this is R. And here we are having a capacitor. Okay.
Yes, sir.
So this is C. Here it is R, and current we are interested, na?
Yes, sir.
So I is equal to what? It is equal to steady state current. That is a VS by R.
Okay, sir.
Not steady state. That is your initial current, VS by R. Okay.
Initial, yes.
Into what? This is equal to your e to the power minus t by tau. This is for RC circuit.
Okay, sir.
And for RL circuit, it is like this.
Tau, 1 minus, yes.
No, tau means time
yes,
constant.
Sir. Yes, sir. RC for yes. This and L by R for other.
L by R, right? And for RL, whatever just now I wrote, na?
Yes, sir. Yes, sir. That is.
That you can use directly, okay?
Yes,
to
sir.
save the time. VS.
And
yes. Next.
Another, sir, one.
Yes.
Sir, one problems associated with series connection of SCR ones.
Just a minute. Problems associated with the series connection of SCR. Yes.
Sir, here you have said that leakage current is less for this VT1.
Leakage current is less for VT1, right?
Yes, sir. So here you have taken a one single current and drawn a line parallel to the x-axis and took the leakage current, sir.
Yes. Leakage
So-
current means this is the leakage current.
Okay, generally which is okay. Sir.
Because in static wave characteristic we are having a forward leakage current.
Yes, sir. Yes, sir.
That leakage current is here.
Okay. If we take if parallel to the same line, we get both the leakage currents equal, no, sir?
What? For parallel?
If we take a line parallel to the x-axis at this black point, you have taken one and drawn to
Here,
VT1.
whatever the
Yes,
line I
sir.
have taken.
Yes, sir.
Ah.
So then we would get both our leakage currents same, no, sir?
Both are the leakage current same, na?
Yes, sir. If we
No. But what I am saying, here the purpose of this taking this parallel line is to check the voltage blocked by the respective SCR, na?
okay.
So from
Yes,
that,
sir.
how we can conclude the VT1 is greater, na?
Yes, sir. Yes,
But
sir.
VT1 is greater, but corresponding to VT1,
VT1,
corresponding to T1,
leakage current is less.
less,
Yes.
right?
Yes, sir. Yes, sir. Okay.
Sir, in the pulse
Another
transformer
one?
question,
Sir, another
Ah,
one.
yes.
Sir.
Yes.
Symmetrical arrangement of SCR you have can you open it?
Yes, just a minute. Yeah, symmetrical arrangement of SCR here.
For above this, sir. First diagram you have taken. Asymmetrical.
Asymmetrical.
Yes, sir. This left side you have tapped the inductor, no, sir. Is it possible to tap that inductor like this?
Yeah, we can connect the inductor.
Tapping of inductor, is it possible?
Yes,
sir? Like-
here, na, here.
Yes, sir.
Tapping.
Yes, sir. Yes, sir.
We can take, because these are not very less turns inductor, right? These will be having a great current ratings.
Okay. Or directly, if we take a inductor and we can tap it directly, you are saying that's it, no, sir?
No, we require actually the specially designed inductors. We cannot directly tap here,
Okay, sir.
right? Just like your transformer that
Yes,
will be having
we
the
can
sequence
tap
of-
the center tap transformer like that.
Yes. So like this we require here.
Okay. Specially designed. Okay.
Yes.
Okay, sir.
sir,
Sir,
pulse transformer
doubt,
question,
Please one by one.
pulse
sir,
transformer question,
Which question?
pulse transformer.
Pulse transformer question. Just a minute. No. Yes.
Sir, in the circuit,
Yes, here it is.
sir, in the circuit, when the base will get current high, then the switch will be open, right?
What the thing? Base?
Sir, the BJT, below we have BJT, na? So
Okay,
this
means for this
BJT,
part you are saying.
yes, sir.
Ah,
So when
this
we
will
are
be open.
sending, so when the pulse sending to the base will be high, that time the switch, the BJT switch will be closed, right?
Yes.
So that time current will not flow through diode; it will directly flow from the
Current will
inductor,
flow only through this loop.
and when it is switched off, it will flow through diode.
That is the thing, but the case is here they have not shown the inductor here, na?
Yes, sir.
If the inductor is there, then definitely that will be there.
Okay, so continuous path, the diode has been provided.
Yes. For continuous path they have provided. Means it is like, suppose if the magnetizing inductance is there, then it will during this, when transistor is in on state, then at that time the current flowing through the magnetizing inductor will be in the downward direction. So that's
Yes,
why
sir.
in order to release the energy, na, your magnetizing inductor will complete the path through this diode.
Yes, sir.
That is
Sir,
when
how
transistor
is,
will be in the off state.
yes, sir. Sir, how is capacitor voltage equal to 1 volt?
Capacitor voltage not here. This VGK is 1 volt. Indirectly, you can say the capacitor voltage also equal to 1 volt here, because it is connected in parallel with the capacitor, na. And this
Sir,
capacitor is only given only they have placed here to tell us that the voltage across gate and cathode is maintained constant, because they have not given the value of the capacitor at all.
Yes, sir. So already when it is given in the question that gate cathode junction during on state has 1 volt, so
Yes.
having capacitor is useless, like it is of no use as such.
No, but how the gate cathode voltage you will maintain constant? With the help of capacitor only, na?
Yes, yes, yes. Got
Otherwise,
it, sir.
it will be changing, na?
Yes, sir. Yes, sir.
Right?
Got it.
Okay. Okay.
Thank you, sir.
Sir,
Yes, Rick.
I have a doubt on this pulse transformer, sir.
Impulse transformer. Okay.
Sir, it's regarding its working, sir. Actually, if you see the major problem with DC is we only have those sharp impulse points, no, sir. That will only come as in the secondary side, no, sir.
This one 9 volt is
Sir, actually, if you look at if you it is going by the law of M di by dt, no, sir.
okay.
If you go like that, there's only changes in the when it is transitioning from 0 to positive and then positive to 0.
Okay. Yes.
So in the output side, we should get only impulses, no, sir.
At the output side, you will be getting only impulses.
Then
That is what we require now. We require gate pulse, na? Whether we
gate pulse
require a
has-
constant gate current? No.
Oh.
We require gate pulse, na?
So just a small like impulse, like small width of very small width.
Yeah, it depends on actually the impulse means you are saying like this.
Yes, sir. Impulse
Right.
ideally is 0 time.
Yes. This type you are saying.
Yes, sir.
But this is also sufficient to trigger our SCRs.
Oh.
Right?
Yes, sir. And like as you mentioned, if there was an inductor there, then wouldn't it be an approximately like decaying current will come in the output side, no, sir, for gate?
Yes, yes, yes. But for that, actually, this diode we connect here, na? In order to avoid that leakage current, means reverse current. That is the
Alright, sir.
detailed actually. But for DC to DC, that isolated type, you will get this idea better,
Okay, sir.
right?
And sir, yes, sir. And there's a next is a symmetrical arrangement of SCRs.
Symmetrical element of SCR. Yes.
Sir, actually here you said regarding this inductors being used in controlling the IT1 and IT2.
Yes.
Sir, so actually, if I'm right, there's a working is like if suddenly if IT2 increases, this V2 will oppose the change in IT2, so IT2 will reduce. So this IT1 will increase, and again V1 will try to reduce this IT1. So at the end, they'll both balance and become equal.
Yes. Actually, the thing is, if the IT1 and IT2 both are same, then it is like there is a no means total voltage across the inductor will be 0 only. Means just like our normal operation. But if there is a difference, na, then only the EMF will be induced.
And that EMF will oppose the current, that is change in current caused due to the temperature change.
Change in the current due to the change in a load actually. The thing is, suppose the load changes na. Suppose a load, suppose we are having a string current, initially it is a 500 ampere. So consider both the thyristors T1 and T2 are carrying a 250 ampere, 250 ampere. Let us consider.
Okay, sir.
But suppose if the load current changes from 500 to 600, then there might be chance that one will share more current, second one will share less current.
Okay, sir.
Right? So that's why in order to reduce the current of the thyristor, which is carrying more current, and in order to increase the current of the thyristor, which is carrying less current. So for that we have placed here inductor.
Okay, sir. And
Incidentally,
sir,
V1 will, if IT1 is more, then V1 will oppose that IT1 to reduce.
okay, sir.
Right? And V2 will.
And sir, then regarding the static,
yes.
sir. Then the static equalizing circuit, we considered only in one of the thyristors, we are considered only minimum current.
Yes, yes, yes.
And rest we are considered maximum. That's any
Actually,
reason,
the thing
particular
is,
reason?
no, actually the thing is like for n thyristors, it will be very difficult to consider the IBA different leakage currents for all the n thyristors. So we are considering just like a worst case. Worst case means what? It is like only one thyristor is having is carrying a lesser current, and other are having some maximum and the same leakage current. So this type of case were considered.
Sir, but again, when these things are in series, shouldn't all of them carry the same leakage current?
Why? These things are series means with R you are saying or without R?
I mean, without R.
Without R you are saying yes.
Sir, without R, I'm saying that if they are all in series and if by default, by some like what you said, like worst case, then shouldn't, it's a series circuit, so current is same. Then shouldn't the leakage current of all shouldn't be the same?
Okay, okay. But the thing, whatever we discussed just now before this, let me tell you. Yes. Here, what we discussed, even though these two are in a same, okay, these two are in a series, right? They will be carrying, but that here IBMN means it is not like that. They are carrying the actual current. That is like your leakage current. I am saying. Means
That
here,
is happening inside the SCR.
No. It is not happening inside the SCR. Please don't get confused. Now you can check here. Here we are having the circuit of two thyristors.
Yes, sir.
These two are carrying a current of this much only.
Okay, sir.
Right now, corresponding to both are carrying the same current, no problem. But what is happening? This second thyristor is having a more leakage current compared to that of the first thyristor.
Okay, sir. Okay, sir.
On static wave characteristic, I am saying.
Yeah.
Actually, they are carrying the same current, but they are, what about their leakage currents?
Okay.
One is having more, second one is having less, and that IBMN and IBMX is there now.
Yes,
That indicates, yes, that indicates the leakage currents of your thyristors.
Okay, sir. Okay, sir.
Right?
Yes, sir.
Sir, hello, sir.
Yes, please.
Sir, in numerical one, can you open, sir?
Yes. Numerical one.
When SCR is on state.
Protection.
This.
SCR protection,
na? Yes, sir.
Yes, in this.
Sir, this one not, sir.
Just a minute. This one, na?
Yes, sir. This one only, sir.
In that.
When SCR is in on state, can you open that?
SCR is in on state then?
You have not drawn the diode, no, sir. Diode will be in short circuit, no, sir. Why you have not drawn the diodes?
Okay. When SCR is in on state, you are saying, na?
Yes, sir.
Actually, look how the circuit operates. Let me tell you first. The thing is, suppose SCR is in off state, then definitely diode will conduct and capacitor will getting charged, right?
Yes, sir.
When SCR is in on state, it is like here it is plus, here it is minus, na?
Yes, sir.
Capacitor was charged to the voltage of Vs volt plus minus Vs volt, na? So that's why this plus will appear here. So can we say that this diode will be in the reverse bias mode now? And you can check if SCR is on, this minus will be here, the minus, same minus will have same minus. Means whatever the voltage across capacitor is there, that voltage will appear as a reverse voltage for the diode, na?
Yes, sir. In off state also, it will be like that only, no, sir.
No. In the off state, it is not like that. When SCR is in an off state, na, then what is happening here? This diode will be in the forward bias mode. You can check. Now, when SCR is in an off state, this negative will not appear at this anode of the diode. Simply diode will be in the forward bias mode like this. Right?
Okay.
And when it is
Okay,
on
sir.
state, then it is like
Sir,
capacity charges and those things. Okay.
okay, sir. Again, one more doubt, sir. In a two transistor analysis, you said, no, sir, on Monday class, you
Transistor
said.
analogy.
Yes.
Yes, two transistor analogy. In that,
if gate current increases, then emitter, then IE2 will increase, no, sir. Then gain should decrease, no, sir. Then alpha 2 should decrease, no, sir. Why it is increasing, sir?
no. Just repeat. Will you please repeat? When gate current is increases.
When gate current is increasing, then IE2 will increase, no, sir.
IE2 increase, yes.
Then alpha 2 should decrease, no, sir.
Why?
Sir, gain
We're
means,
having here IE versus alpha. Na?
yes, sir.
If IE increases, alpha should increase or decrease,
Oh, okay, sir, should increase.
right? So
And-
that's why your alpha 2 is increasing.
Okay, I thought generally alpha means IC by IE, no, sir, like that I thought.
No. Actually, this is the we are having the reference of this plot, right?
Yes, sir. Okay, sir, understand. Again, one more
Yes.
doubt, sir.
Yes. Please.
Sir, when the current in SCR is less than latching current, then SCR will turn off, sir.
When current in SCR is less than,
Latching current,
okay,
then SCR will turn off, sir.
no, let me clear first. Whether your SCR is in a on state or not, on state.
Yes, sir.
Okay, if SCR is in a on state, and just now if you have triggered it with the help of gate signal, na,
Yes, sir.
and at the instant of removal of gate signal, if your SCR current is less than the latching current, then our SCR will turn off. But suppose if you have removed the gate signal previously, and currently your SCR is working fine, on state only, right?
Yes, sir.
Then if the latching current is flowing through the SCR, then also SCR will be in the conduction mode. But if current is less than the holding current now, then your
Yes,
SCR will turn off.
Okay. Sir, why latching
where-
current?
Yes,
Yes.
please. Huh.
Why latching current is more than holding current, sir? I didn't get that one.
Generally, you can check na. Latching current is associated with your just turning on of a SCR, means where the depletion layers were already present, right? And at the instant of starting, the current you require that will be slightly more than that of once SCR turns on, means depletion layer will be not present now. Yes, all the three are acting as a short circuit. Then in that case, whatever the minimum current required to maintain SCR in the on state, okay, that will be your definitely less than that of whatever the current you are having at the instant of starting.
Okay.
Because at the starting only you require a more current, na, more force you require, more current you require. Once it is
Okay.
working fine, once all the depletion layers are widths become zero, all are acting as a short circuit, right? Then after that we require, suppose the current is slightly lesser than that of latching current, then also our SCR will continue maintain into the on state.
Yes, sir.
Right? This is during at the starting we are having, so that's why that current is a little more. Okay.
Okay, sir. Sir, again one
Yes.
more, sir. What is
Yes.
the difference between TC and TQ, sir? Both are turn off times only, no, sir?
No. TQ is a device turn off time. Means for a device to turn off, how much time is required? That will be your TQ. And TC means if you recall the dynamic characteristics of the SCR, in that we are having a TRR plus TGR.
Yes, sir.
TRR plus TGR means your TQ. Okay.
Yes, sir.
And TC means if we want to successfully turn off the SCR, then we need to maintain the SCR reverse voltage across the SCR for the minimum time of TQ. But that should be minimum, I am saying. Okay, if you maintain the reverse voltage across SCR for a time less than the TQ, your device will not turn off successfully. So device has not successfully turned off, the meaning is if I again apply the forward voltage now, then my device, without applying the gate signal, my device will turn on. That is nothing but device has not successfully turned off. This is actually meaning. And circuit turn off time is what? The time for which we maintain the reverse voltage.
Okay, sir.
Both are different things. One is given by the manufacturer. Second one is selected by the design engineer. But definitely the design engineer should take the help of TQ only in order to set the TC value.
Okay,
Right?
sir. TC means the time taken to maintain the reverse voltage. TQ means
Yes. TC means the time taken, time for which the reverse voltage is maintained. That is a TC.
yes, sir.
And TQ means for the device, okay, whatever the time is required to turn off, that is a TQ,
Okay, sir.
right? Yes.
Hello, sir.
Next. Hi,
Sir,
yes, please.
sir, when you have discussed about thermal stability, you have said that the curve is square, but at the end of the edges, we have more power loss. So we'll cut that, and you said that the curved shape, no, sir.
What? Please repeat.
Sir, when you have said about the thermal stability, that square curve, sir, means you have said no, sir. V max and forward voltage max and current max, sir.
Thermal stability.
Yes, sir. Thermal stability region
At
of
the
a
beginning.
device.
At the
Yes,
beginning.
sir.
Means you are saying thermal
Yes.
stability, not the thermal modeling. Okay.
Yes, sir. Sir, there you have
Yes,
said
yes.
that the peak points of V max and I max we should not operate, and that we should cut that portion and we should operate below that. No, sir.
Average we are having.
Sir,
This not P average cross curve is there.
no, sir. At the starting class you have said no, sir. Thermal stability. The
Just
thermal
just-
stability
just-
region. Yes.
Let me open it. Let me open it. I think in this it will be. I think here it is only. Yes, here it is.
Yes, sir.
In
Sir,
this-
sir, in this the top portion of edge, sir, the top edge,
Hmm.
we
This
should
one.
not operate on that right side, sir.
This I dash now or this one?
Yes, sir. We should
Huh.
not operate there because power limit is maximum there. You said no, sir.
Yes, yes, yes.
Sir, but both forward blocking voltage maximum and forward conduction current maximum both will not happen at the same time, no, sir.
Okay, okay. Means you are saying both are not happening at the same time.
Yes, sir.
Okay. The thing is, look, these two will not happen at the same time because this is like your I dash means what? It is like a maximum current that can be flowing through the device.
Yes, sir.
And it is like a maximum voltage that can be blocked by the device. Okay.
Yes, sir.
Right. So
Yes.
yes, whatever you are saying it is correct. Right. This is like a current limit, and this is for your yes, current limit. Right. Yeah. No, but it is not like that. The meaning is we should not operate here.
Yes, sir.
Just a minute. Let me. You good question you have asked, right? Before this, none of my students had asked, right? This is during the blocking state, and during the blocking state, definitely this much current will not flow. That is true. Right. Yes. The thing is actually here. If we operate here, okay.
Yes, sir.
Maximum voltage, suppose maximum current is flowing here through the device. When the current is flowing, that's the voltage will not be that much. Right. Will you please give me some time? I will let you know by tomorrow.
Yes, sir. Sir, okay, sir. Then
Right,
I'll ask
right.
another doubt, sir.
Right. Because if it is not operated here, then definitely here it will not be operated here also, right?
Yes, sir.
Because
Sir,
the
I'll
same current
and I
here,
have
no?
yes, sir. Sir, I have another doubt, sir.
Yes, please.
Sir, you have discussed about gate cathode circuit characteristics, no, sir.
Yes.
There you have drawn one curve, sir. Once open that.
Gate cathode circuit. Just a minute. Yeah, gate cathode characteristics. Yes.
Sir, that graphs are between IZ max and VZ, sir. IZ and VZ.
Yes.
Sir, you have drawn that yellow lines, no, sir. For
Yellow lines.
temperatures.
Yellow lines, huh?
That means the lines are going up, no, sir, when the temperature changes. But what when the temperature increases or when the temperature decreases, the curve will go up, sir. What is the relation with temperature, sir? There.
Okay. No, actually the thing is, if temperature increases,
Yes, sir.
then it is like your current carrying capacity. okay, or your current, that will be reduced, that should be reduced, because our semiconductor devices are having thermal stability issue. Means if the already temperature is high, for example, suppose if already temperature is high, and if we are increasing the current further, na, that IC suppose,
Yes,
then
sir.
what will happen? Again, the temperature will increase. So it will be like A, B, C from here to here. So it will be like a temperature is reducing, right?
Yes, sir.
This should be like from A, B, C, that will be reducing.
Temperature is reducing. Okay. Means
Then only
but
then it is possible.
sir, but you said that it has negative coefficient. No, sir. Negative coefficient of temperature.
No, no, no. Already temperature is high, I'm saying.
Yes, sir.
And if I want to operate at a more current, in more current, then again
Yes,
the
sir.
power loss will increase.
Yes,
Power
sir.
loss increase means again heat will increase, again temperature will increase.
Okay, sir. Okay.
So corresponding to the high temperature, I need to circulate a less current only, na?
Yes, sir.
Right? Okay. Means actually what the manufacturer does, for a specific temperature, he
Yes, sir.
operates our gate cathode circuit, and accordingly he draws these curves. Okay.
Yes, sir.
Right? Yeah.
Sir, and another one, sir. Why the low line is straight one, sir?
The load line, generally load line we draws this only this way, na? Well, that is
Yes,
the
sir.
peak point of voltage, peak point of current, and after that, when to miss, it indicates our operating points of our circuit, operating points of our circuit,
Okay, sir.
right?
Hello, sir.
Yes,
Yes,
sir.
please.
Hello.
Yes, please,
Sir,
please.
Sir, the last problem, pulse width module. Sorry, that
Pulse
is
transformer.
pulse transformer, sir.
Just
It
a
was
minute.
it was clear in the question itself that we have to take the maximum voltage. Voltage supplied. However,
Yes.
if nothing is given in the question, what should we take?
Okay.
What voltage we should take if we have to calculate the rating?
No, then also we need to take the maximum only, because as per the definition of that volt second rating,
Yes, sir.
it is like the maximum possible voltage, maximum voltage applied, that only we need to take.
Okay, sir. Another
Right?
doubt was, sir, in problem just before series connection of SCR, the protection circuit problem.
Just a minute. Protection of the SCR, na?
Yes, sir.
Okay. Protection of SCR. Yes, here it is. Number one, number two.
Number two,
Which
sir.
problem?
Number
Yes,
two, sir.
here it is. Yes.
Sir, in this case, while calculating DIL by DT, we were choosing the worst case scenario.
Yes.
Should not we choose with RL is equal to 0, so that the worst case scenario would be quite good in that case?
RL means your load register.
Yes, sir.
No, the
If you
actual
are
thing is whether your register is affecting the change in the current or the current wave shape. No, resistance will only affect on the magnitude of the current, right?
Yes, sir.
Resistance will not affect on the nature of the current, right?
Yes, sir.
But your capacitor is affecting the nature of the current. So that's why we are removing it.
Okay, sir. Sir, in this problem itself, why while calculating VT is equal to ILRS, why we are neglecting capacitor?
VT is equal to yes, this one, na?
Yes, sir.
VT is equal to IL into RS.
Yes, sir.
This one, na?
Yes, sir. Yes, sir.
Okay, okay. Now we are neglecting the capacitor, means the same circuit we are only proceeding here. Right? Because
why
worst
so, sir?
case, this is a continuation. This is a continuation of that your worst case. So that's why you are neglecting it. This is.
Okay, sir.
Right?
Sir, another thing was that, sir, should we not take diode across RS for having worst case scenario?
Diode across RS.
RS. As we are not
Hmm.
given any circuit diagram regarding this question itself.
Okay. Yeah, that we can, but the thing is, as long as the data is given, okay. Generally, while designing the inductor, di by dt inductor, okay.
Yes, sir.
What we are considering that we don't know, means when manufacturer designs a particular value of the selects or you can say calculates a particular value of inductor, he doesn't know, means that capacitor will be connected to which type of load, which type of circuit, yes or no?
Okay,
But the
sir.
minimum things are definitely this is for your R and C calculation, that is the snubber circuit calculation, that will be there only, and inductor will be there. So which elements will be affecting your current here, then that will be your capacitor and inductor only, that you he is going to consider. Definitely, if you
Okay.
consider the diode across the RS, na,
Yes, sir.
right? Diode across the RS. The diode across the RS will only what that diode will do, that will provide the path. Again, there also you can check, even though resistance is considered RS, or you are across the RS, you can consider the diode also, whether it will change the rate of change of current. It will affect on the rate of change of current, it will not affect, na?
Okay, so it will not affect the maximum amount. The maximum
No,
rate of current, it will
but
not.
I'm saying for that curve means rate of change of current, I'm saying.
Okay, sir. Okay.
Just like a capacitor is directly changing your nature of the current, because as capacitor go on charging, it is opposing more and more, na?
Yes, sir.
But in the case of diode, what is happening? Instead of RS, you are saying the diode, suppose if it is connected, the only thing is overall path resistance will decrease, but your
Yes.
slope of that curve, it will not affect much, right?
Okay, sir.
Okay.
Sir, another doubt was in string efficiency problem
String efficiency, okay.
just before pulse transformer problem.
Just before,
Pulse transformer problem. Pulse transformer theory part.
yes, this is na.
Yes, sir. Here, string efficiency was given 100%, and we
90%.
said second problem, sir.
Whatever the I have considered, okay. Means I discussed that problem additional, okay, huh?
Sir, here string efficiency is 100%, and it was said that the each SCRs will be having rated voltage across it. How it is
Yes.
going to happen, sir? As the characteristic will be different, and voltage drop across
No,
each SCR will be
that
different.
characteristic is not string efficiency 100%. The meaning is characteristic is not different, na?
How, sir?
You can check. Suppose string efficiency means we are having like this, okay? So what is string efficiency? Percent string efficiency, right? Is equal to what? Your string voltage divided by number of SCRs, na, N,
Yes.
connected in series, into voltage blocked by each SCR, or voltage rating of each SCR, right?
Yes, sir.
Each SCR. So you can check if this is 100%, string efficiency is 100%, means it is like a 1, na? So
Yes,
that
sir.
we can write it as NS into voltage blocked or voltage rating, you can say, okay, by each SCR is equal to what? String voltage. So now what is this voltage? String voltage divided by NS, na?
Yes, sir.
So all will share equally voltage.
Okay. That means as string efficiency is 100%, that means the voltage blocked by each SCR will be rated voltage itself. This implies that the characteristic will be same, right, sir?
Yes, means it here we have said that minimum 5 we have connected in series, because each is blocking, we are considering each can block 1 kilovolt, na? So that's what total will be like your, and they have given 1 kilovolt, na? So that's what total will be, we require 5 SCRs. But suppose instead of that, if they said that 6 SCRs are connected in series and each is having a 1 kilovolt voltage, 1 kilovolt voltage rating. and total string voltage is, if it is 5 kilovolt, then each SCR will be blocking a voltage of 5K divided by 6. In that
Okay.
case, it will not be 1 kilovolt. Are you
Okay,
getting the
that
point?
means the each SCRs are at the verge of its blocking voltage VBO, right, sir?
Yes, yes, yes. Now,
Okay.
now this is at the VBO,
Okay, thank you, sir.
right? Right.
Hello, sir.
Ah, yes, please.
Sir, in the static equalizing resistance, sir, there we took 2 SCRs. So, sir, there,
Static. Yes, yes.
Sir?
Please go ahead. Go ahead.
so sir, there we are taking, sir, what do we want? We want the voltage to be same across each SCR, or we want it to be proportionate to the rating of that SCR.
Will you please repeat? In
Sir,
static equalizing circuit,
yes, sir. In this, our sir, what is our aim in this? We want the voltage to be same across both the SCRs, or we want it to be we want the individual voltage proportionate to the rating of the each SCR.
it depends on, suppose if all your n SCRs are having the same voltage rating,
Yes,
then
sir.
it is like a equal voltage sharing is required. That is the ideal case.
V by 2, V by 2.
Yes, yes, yes. It is like V by 2, V by 2. But suppose if you are having the two SCRs, one is having a, let us consider 1 kilovolt voltage rating, and second one is having a 1.5 kilovolt voltage rating.
Yes.
Then
sir.
that should be in proportional to their rating.
Okay, so the voltage sharing will be proportionate to the rating.
Rating only, right? If all are having the same voltage rating, then definitely they should share the equally, right? And if they both are having, suppose we don't know na string voltage what might be, and what is the available voltage rating of the SCR. It is not like that the manufacturer can produce a 1.5 kilovolt also blocking voltage rating SCR, right?
Yes, sir.
It produces the SCR voltage blocking like 1 kilovolt, 2 kilovolt, 5 kilovolt in that term, na. So suppose if
Yes.
my string voltage is like, for example, suppose 6 kilovolt, then how many number of SCRs we need to connect? That depends on available SCR voltage rating, right? And
Yes,
accordingly,
sir.
we need to select the number of SCRs we require to be connected.
Okay, and sir, in the second numerical after
Yes.
this protection, second numerical,
Second numerical protection, yes.
sir, in that I also have that question that RL should be, this SCR should be before RL because sir, and RL should be after RS because they have also mentioned that SCR is between the source and
Which you
SCR
are
is
saying that
between.
this SCR and this branch RSCS should be here
Yes, sir, it should be before RL.
before RL. It doesn't matter. Anywhere you can connect now, because this is like a series circuit only.
Yes, sir.
It doesn't matter whether you are connecting here or here, right? Means I'm saying whether you are connecting here or you are connecting here, it doesn't matter.
Yes, sir. If we connect before that, then we don't need to take RS plus RL. So then RL will be automatically, we don't have to take
Then-
that in the calculation.
Then we need not to connect.
Sir, we will not need to take RL in the calculation. Sir, in IL we have taken RS plus RL. And then we
Okay,
ignored
means-
RL equal to 0.
No, they have not given the RL value, na. That's why
Yes.
we ignored. No? Ignored.
Okay, sir, can
Anyways,
we?
RL, you are it connected here or here or here or here. That will be, that RL is going to oppose your current, no problem. That RL is going to oppose your current anyway.
Okay, sir.
Because when SR is in a off state, now when SR is in a off state, the current will be flowing in this branch only, na. Current will
Yes.
flow through RL also, L also, RS also.
Yes, sir.
So that's why the RL is going to oppose your current, whether it will be connected here or here or here, doesn't matter, right?
Okay, sir. And in this numerical only, sir, we have taken that IL equation, Vs upon,
Yeah.
sir, that steady state part. So how that equation, sir, this, yes, sir, this IL, sir,
Just a minute. Here, I think here it is. Yeah, this one, na?
yes, sir, Vs
Here it is.
upon, yes, sir. Sir, how?
Okay. Actually, for RL circuit, always keep it in mind. The final current final current in the circuit, okay, is equal to supply voltage divided by resistance
Okay.
into 1 minus this e to the power t by tau.
Okay.
Okay, means suppose one of the student also asked this same. I have added one here. Not here, just a minute. Here. Yes, in this. If the circuit is a RC, we're having the standard expression is like this. You can check, apply KVL. You can do the your Laplace transform. Okay, and after taking inverse Laplace again, you will be getting this expression only, right?
Okay. Okay,
Is
sir.
equal to RC. And similarly for RL, we are having it is a I is equal to Vs by R. Okay, because at steady state, what is happening? Your inductor is lightly acting as a short circuit, na? In transient, you might be come across this term,
Yes.
this thing. At a switching instant, inductor acts as an open circuit. But at steady state, inductor acts as a short circuit. So when inductor acts as short circuit at steady state, you will be having current like Vs by R only. So it is a Vs by R. Into what? It is like a 1 minus e to the power minus t by tau we are having. And tau is equal to L by R.
Yes. Okay, sir.
Right?
And sir,
Which thing
last
we are having?
question. Yes, sir. Last
Ah.
question. Sir, can you repeat that in pulse transformer we are providing isolation between the two, so because of high current. So
Just-
can you just repeat that
just a
part?
minute. So pulse transformer, no difference between, yes, here it is. In this,
Yes, sir. Only that part that we are connecting it between these two for isolation to avoid high current. So can you repeat
Yes.
that part?
okay. The thing is actually between anode and cathode, we are having a high voltage, high current circuit.
Yes, sir.
And here, if you remove this symbol, na, in this symbol, what we are having? We are having the actual construction of the SCR. There we are having a PN device. Yes or
Yes,
no?
sir. Yes.
So we are having this type of circuit, PN. Okay. And here we are having the low voltage between gate and cathode. This is a gate. This is a cathode. Here we are having the low voltage, low current supply. And here it is a, yes, we are having a high voltage and high current. So this current is a IA. That is a high current. Yes or no?
Yes,
So
sir.
you can check here, this cathode terminal, right? This gate current is also flowing here. And this IA is also flowing here through this terminal.
Okay.
Right?
Okay, sir. Yes,
And
sir.
this part, right? This part, sorry, gate should be here actually. Let me correct it, right? This is a PN, na?
Yes, sir.
So gate should be at the upper side, right? Gate should be at the
Yes.
upper side. Please consider here gate.
Yes, sir.
Gate is not here. So it is like, if you consider this part of the device, na, it is coming across at one side, it is having a high voltage, high current. And at this side, it is having a low voltage, low current,
Low current.
right?
Okay. Okay.
So that will create a problem for the device.
Yes,
So that's
sir.
why we need to isolate this. And generally in electrical science, we are isolating the low voltage and high voltages.
Yes, sir. Okay.
So that's the same thing here. We need to, for that, we need to use the pulse transformer here,
Okay. Okay. Thank you, sir.
right?
Thank you.
Okay.
Hello, sir.
Yes.
Sorry,
please.
sir, you said in dynamical equalizing circuit, you consider capacitors across SCRs, no, sir?
Dynamic equalizing circuit. Yes. Just a minute. Let me open it. Yeah, dynamic equalizing circuit. Yes, here it is.
Sir, you have said one point like absorption of charge carrier, sir.
Yes.
Once you can elaborate it, sir.
Okay.
Sir,
The thing is, what is happening? Two SCRs are connected in series. But
Yes, sir.
this SCR is having a less number of reverse recovery charges. So that's why this will
Yes,
turn
sir.
off first compared to this thyristor. So whatever the string voltage is
Yes,
there,
sir.
that will appear across the thyristor T1, and our thyristor T1 will be in problem. Okay, it may get damaged, or it will be over voltage will appear across this thyristor, or it will be over stressed, we can say, right? So now for
Yes,
that,
sir.
what we are doing? We are connecting a capacitor here and here as well. Because in real life, we don't know na, whether it is having a
Yes, sir.
more QRR or where it is having a more QRR. So we are yes, keeping the capacitor across both the you can say both the thyristors. Okay. So if this is the thing, then
Yes,
what
sir.
will happen? You can check when the reverse current will flow na. When the reverse current, you can check QRR means what? You are having the reverse current. So suppose
sir.
if this thyristor is having a more reverse leakage more QRR, reverse recovery charges more. Okay. So that's why this
sir.
capacitor will absorb those charges fast. This capacitor will absorb those charges fast. So that,
Yes, sir.
the resultant turn off time of the thyristor T2 will be reduced by some extent.
Okay, sir.
Because capacitor, we know capacitor is the element which can store the charge, means indirectly it can absorb the charge.
Yes, sir.
This is the one way you can think. Or the second way we are having is, this is connected across this each SCR capacitor, and capacitor is having
Yes,
a
sir.
basic tendency that it opposes the change in the voltage.
Yes, sir.
So now when this thyristor turns off, when T1 turns off, so suddenly voltage across T1, string voltage will appear across the thyristor T1. But due to this capacitor, because capacitor is connected in parallel with the thyristor T1, so that's why whether this capacitor will allow the sudden change in the voltage across thyristor T1? No.
No.
So in this way, this capacitor can protect our thyristor T1.
Okay, sir.
Right?
Thank you. Yes, sir. Thank you, sir.
Yes. Yes.
Sir,
Next, Gopal
Sir.
Krishna. Yes. Yes.
sir, please
Yeah, one
open
by one, anyone, please.
second numerical in SCR protection, sir.
Second numerical in SCR protection. Just a minute.
Calculation of L, sir.
Calculation of
L,
okay.
where we started C. Sir, we are placing that inductor to avoid rapid change of current through SCR at the time of turning on the SCR to avoid damage due to hot spots, sir. So we have to consider that SCR turned on, sir.
No, the thing is actually they have already given the di by dt withstanding capacity of the thyristor, na?
Okay.
Now we are
we have-
designing the inductor that should be able to block if the di by dt will be greater than that of whatever the that can be withstanding the capacity of the thyristor.
When we are calculating CS, we are taking SCR in off condition. When we
Yes.
calculate di by dt, we have to consider SCR in on position, sir.
No. Actually, the thing is, you are saying that definitely whatever you are saying that key when SCR is in because basic purpose of the inductor is to avoid the false triggering or to avoid the damage.
Damage.
Okay? Right, and the damage will be only when at the start
SCR
of the when we inject the charges into the P2 layer, na, at that time
Yes.
there will be the one hotspot will be created. Okay, and due to that will be happening. Is this clear, na? So now here the thing is we are designing the inductor now. We are
Okay.
not designing the thyristor now. We are designing the inductor. Already we know the maximum di by dt value with which the thyristor can withstand, that we know. But now
Okay, sir.
our task is if the di by dt is greater than that of whatever withstanding capacity of the thyristor, so what will happen? So for that we need to consider this inductor, and this inductor should not allow the di by dt to be greater than whatever the capacity or di by dt capacity of the thyristor. So now
Sir,
think only for the inductor. Don't confuse it with the thyristor. Thyristor
Sir,
we are already having that di by dt capacity.
Sir, assume let the thyristor don't have dV by dt protection, sir. In this question, how to find L value if
Okay,
they given di by dt?
Okay. Then in that case, simply we need to means only inductor is there, and if di by dt is given, na, then only thing is we need to check for the voltage across the inductor at all.
Okay, sir.
Because here if R and C are not there, right?
Hmm.
Then the only thing is what we can do, V is equal to L into di by dt, na?
Yes, sir.
So we need to check only the maximum voltage across that can be appeared across the inductor. And at what instant the maximum voltage will appear? That is at the instant of switching, that is at t is equal to 0 only, na?
Okay, sir.
Because at t is equal to infinity, your inductor will act as a short circuit.
Okay, sir.
Right? Okay.
Hello, sir.
Yes, please.
Sir, in this question itself, I did not understand why did we short circuit that capacitor.
Okay. No, actually the thing is, keep it in mind. Here our task is to design the inductor. And
Yes.
what is the purpose of the inductor? The purpose of the inductor is to oppose the di by dt or to limit the di by dt, right?
Yes, sir.
So here, if you check this inductor, and here this capacitor is also present. This capacitor will oppose the change in the as the capacitor go on charging. Definitely, this capacitor will oppose the current, na? Suppose here it is 0 volt. Suppose now 1 volt will be there. If here it is 1 volt, na, so what will happen? Our capacitor plates, means whatever the charges are present here at the upper plate and the lower plate, these upper plate charges will oppose the additional charges. Those will be again coming to the capacitor upper plate.
Yes,
So
sir.
indirectly, what this capacitor is, what it is opposing the rate of change of current. But in the worst case, we don't know, na. Sometimes suppose if RS and CS is not there, in the worst case I am saying, in the worst case means what? This inductor should what I can say, inductor alone should control that di by dt. So for that, here we need to consider only L, no CS at all. Or even though here you can check load, we have considered the resistive load, na. If they
Yes,
give,
sir.
they would have given the RL load also will help to oppose the di by dt, because in the RL load we are having the inductor, na. So in the worst
Yes,
case means
sir.
what? We need to consider the purely resistive load only, and we need to consider the CS only. CS should not be there in the circuit. That is the worst case actually.
Okay, sir.
Right?
Sir.
Okay.
Sir, and one more doubt. I do not
Yes, yes.
understand why in series connection of this SCR, this leakage current is different for the two SCRs. How it is?
Okay. Series
that,
connection
sir.
of SCRs, na? Yes.
Sir.
Problems associated with in the series connection of SCR. Yes. Here, suppose these two SCRs are connected in series.
Yes,
Right?
sir.
Definitely, they will be carrying some same current, equal current.
Sir.
They are carrying the equal current, no doubt. Okay, and that same current is like this one. This current we have taken.
Sir.
Both the SCRs are carrying this current. Now, corresponding to this current, if you check the operating point for the second SCR, it will be at this point.
Sir.
For the first SCR, the operating point will be at this location.
Okay, sir.
But corresponding to this operating point, what is the voltage across the thyristor T2? It is a VT2.
Sir.
Corresponding to this point, what is the voltage across thyristor T1? It is a VT1.
Sir.
What this indicates, thyristor, definitely current flowing through both the SCRs are same. But thyristor T1 is carrying more, blocking more voltage. Thyristor T2 is blocking less voltage.
Sir.
Why thyristor T1 is blocking more voltage? Because thyristor T1's leakage current is less. Don't get confused. This leakage current, definitely these two will be in the off state, means here also leakage current is flowing, but that leakage current is same only. Here I am saying from VI characteristic, this is the leakage current now.
Sir.
And for thyristor T1, and this is the leakage current for thyristor T2. So thyristor T1's leakage current is less. So thyristor T1's leakage impedance will be more. So thyristor T1 will block more voltage.
Sir.
And opposite for thyristor T2. Thyristor T2's leakage current is less. Thyristor T2's leakage impedance, thyristor T2's leakage current is more. So thyristor T2's leakage impedance will be less. So that's why thyristor T2 is blocking less voltage.
Sir.
Means current is same flowing, but I am saying the leakage impedance, if you compare the leakage impedance of the first and the second thyristor, because you can check second thyristor's characteristic, that is this blue one, is somewhat yes, above to that of your green one. Na?
Sir.
So the leakage current of second thyristor is more, leakage current of first thyristor is less.
Sir, then if two thyristors are having same rating also, won't they have the same leakage?
They are having the same rating. Here you can check VBO is same na for both the thyristors.
Sir.
So they are having the same voltage rating. but they are having the different static characteristics, VI characteristics.
Okay.
So that's why the problem is. And
Sir, so
yes. Yes.
this leakage current, even though it is the same leakage current which is flowing, in one it will be different and the other, and one it will be less and the other it will be more. Is it like that, sir?
What? Please repeat. Please repeat.
Yes, sir. Because it is in series, it is supposed to be that the same leakage current is flowing through both. But then you're telling that through one it is, inside one it is less and inside one it is more. Is it like that, sir?
No. It is. Don't get confused. Through both the thyristors, only this much current is flowing. This leakage current is flowing.
Sir.
But both are not blocking the same voltage. So why the both are not blocking the same voltage? For that we have added this characteristic leakage current. Are you getting the point? You are confusing in this leakage current and this leakage current.
Okay.
Actually, the leakage current flowing through both the thyristors is same only. But from characteristic you can check forward leakage current of this one is here. Forward leakage current of this second thyristor is this much. Okay. Right. So accordingly, VT1 is more. So for that we have written this conclusion. Okay,
sir.
These two are in the same. These two are series means what? Definitely current will be same. And that current, again I am repeating, that current is this current only.
Okay.
But from static VI characteristic, these two are having some leakage, different leakage currents. Now this leakage current, don't get confused with this leakage current, right? Please. Okay.
Sir, and why are we connecting the resistors in parallel to this, sir? That could you explain once again?
Register in static equalizing circuit.
Sir.
You can check that numerical, whatever we discussed, na? Actually, what we're doing, both the SCRs or all the NSCRs we're having, suppose we're having two SCRs only, both the SCRs are having different leakage impedances.
Sir.
So if I connect the same value of high value of resistance across each SCR, then whether it will help to improve the voltage sharing of both the SCRs, definitely. Because you can check in the numerical, whatever we discussed here, we considered 25 kilo ohm resistor connected. Here also 25 kilo ohm resistor connected. You can compare these two. Suppose this SCR is having a leakage resistance of, for example, suppose a 500 ohm here, and suppose here it is a 1000 ohm. You can check, you can draw the circuit 500 ohm, here it is a 1000 ohm. Across 500 ohm, I have connected the 25 kilo ohm. Across 1000 ohm, I have connected 25 kilo ohm. Okay. So now you can check, suppose across both the thyristors, if we connect a 100 volt voltage source, now you can find here equivalent resistance here, and you can check the voltage across this, voltage across this. This is after static equalizing resistance. Sir. And before static equalizing resistance means, suppose if this resistance is not there, consider this resistance is only 500 ohm. And this one, whatever we considered, I think it is a 1000 ohm we consider, right?
Sir.
So 500 and 1000, and across that also you can connect the 100 volt voltage source. And then you can compare both the voltage across this and voltage across this before static equalizing circuit and after static equalizing circuit. You will get improved voltage sharing in this case. Right? Generally, what we do in the network theory, if a high value of resistor is connected across a particular branch, then your resultant resistance, right? Resultant resistance will change. And we are approximating the resultant resistance of this branch, these two parallel and these two parallel. We are keeping nearly equal. Right? Okay. Yes.
Sir, and one last doubt.
Okay.
In one question in which we had 100% string efficiency and we connected in series and parallel both, sir.
Yes.
Sir, so actually is it practical, because 100% efficiency we won't get now, sir?
This is not practical. This is an exceptional only way of consider. 100% string efficiency is not possible in the practical case, right?
Yes. And usually
Yeah,
when we
in order to get the idea of how how many number of SCRs are required now. So for that
Yes.
idea, actually, I discussed that numerically here, right?
Yes, sir. And usually when we give like this also, sir, we should be giving protection also, na, sir, whatever we discussed.
Across each SCR, we need to give the protection also.
Okay.
Yes, because SCR is a very important device for us, right?
Yes, sir.
So that's why we need to whatever till now whatever we discussed, we need to provide the protection. We need to connect the gate cathode circuitry in order to turn it on, right? We need to use the pulse transformer. Everything we need to give to connect to that SCR, right?
Yes, sir.
Okay. Okay.
Okay, sir. Thank you, sir.
Yeah. Thank you. Yes, Salman Khan.
गुड मॉर्निंग सर.
Hello.
गुड इवनिंग सर.
हाँ, आपका नाम बहुत अच्छा है. हाँ.
जी, थैंक यू सर.
Okay. Okay. Yes. Yes. Please.
So in practical condition, when we have string efficiency 0.9, sir.
Will you please speak a bit louder?
Am I audible, sir, now?
Yes.
Yeah. Sir, in practical condition, when example string efficiency is 0.9, sir, then you said that in series, for series we draw separate, and for parallel we draw separate. Means for current we draw separate, and for voltage we draw separate. How did we get overall then, sir?
Actually, the problem is if you check this numerical, right? Okay.
Okay,
So
sir.
we are having the string has a voltage rating of 11 kV and current rating of 4 kiloampere, right?
Right.
And here efficiency is 90% we are having.
Right.
So it is like whether our SCRs are sharing the equal voltages.
No.
No. So and whether our SCRs are sharing the equal currents.
No.
No. So how we can connect them in a one circuit?
Yeah. I'm bothering. Then how will you get this circuit? That's what there is in my mind.
What? How?
I understand that we cannot connect them in one circuit, but in actual condition, how are we going to get this condition, sir?
Okay. In actual condition means we connect like this only, for series different and for parallel different.
Okay, mother, totally different views.
Because for the series purpose is the purpose of the series is like to block the voltage.
Right.
And purpose of the parallel is to allow the current.
Allow the current.
Both are having the different functions. So in
Right.
this case, in practical case, if we want to draw, then we need to connect the 7 number of SCRs, I think, na, for parallel series we wrote na NS.
Yes.
We need to connect 7 number of SCRs in series.
Okay.
Okay. Right, and we need to connect the separate parallel. How much parallel we calculated? 6 or 5, right?
5. Right.
So we need to connect the 5 parallel again.
Yeah.
Right, like this we need to consider. Means it is not like that. I have connected the 5 parallel branches. Okay.
Yeah.
And in each branch, I need to connect the 7 number of SCRs. It is not like that.
Yeah. That's what I was confused about.
Yes. This is
And
the
in,
actually problem in the practical case.
Yeah.
Right?
In blocking conditions, sir, the voltage string will be effective, and in a conduction state, the current string will be effective.
Please speak a bit louder.
In
Your voice
blocking
is
condition.
very less. I don't promise. Just a minute.
Yeah. In
Let me
blocking
check
condition,
whether.
sir, the series connection will be active. Means.
Okay. Yes.
Yeah. And in conduction condition, the current distribution condition will be active, sir.
Yes.
Okay, sir. Okay.
Right.
Thank you, sir.
Okay. Yeah.
Understood.
Yes. Milan Kumar, are you there? Hello, Milan Kumar. Yes. So your question is in series and parallel connection, different rating. Yes, there is connection possible. Yes, definitely possible. Or I can say that in real life, we need to connect the different rating SCRs only in series and parallel, because we don't know na what is the string rating, string voltage rating, and whether for that string voltage rating whether we are having the available voltage rating SCR is there or not, that we don't know na. So for that we need to form the string as per available voltage and current rating only, right? So next, any condition required to series and parallel connection of SCR. Any condition means what? Yes, any condition means no, yeah, I thought like the transformer you are thinking. No, like the transformer, it is not required in this case, right? Because we are having, it is a small device, it is a passive device, and it is having only 3 terminals, anode, cathode, gate. While connecting this series, we need to only think for cathode of one will be connected to the anode of second, like this, right? Okay, right. Thank you. Thanks to all of you. Yes, Madhu Chandra, you are saying, sir, can we say string efficiency does not depend on voltage drop across SCR? Yes, you can say. Okay, because in the string efficiency you can check, we are having the straightforward terms, na? So voltage drop, it will not affect much, right? It will not affect for on the string efficiency. Okay. Okay, right. Thank you. Thanks to all of you.